Hello there and welcome to Life Beyond Scene, where curiosity takes its time and science flows at a gentler pace. Perfect for those moments when the world above feels a little too loud. Tonight we're trading clocks and calendars for currents and crushing depths, drifting far below the surface into a place few have ever truly seen. Imagine the deepest point on Earth, deeper than the tallest mountain is high, a place so remote that light itself never reaches it. That place is Challenger Deep, the hidden trench at the bottom of the Pacific Ocean, a cold and pressurized world that makes the summit of Everest look almost ordinary. And yet, despite its distance, despite its darkness, despite the weight of the entire ocean pressing down, life is there. Not just clinging on, but thriving in ways that challenge everything we thought we knew about survival. Before we begin this descent together, I'd love to know something simple. Where in the world are you listening from tonight? Are you near the sea, where waves lap gently against the shore, or perhaps miles inland, where the ocean is more of an idea than a presence? Either way, the water we're about to explore is closer to you than it seems. It cycles through the air, it hides in every drop of rain, and somewhere out there it's flowing toward the trench we're about to visit. And if this gentle dive into the unknown helps you unwind or sparks a bit of wonder, I'd be grateful if you'd like this video and maybe subscribe. It helps more curious travellers find their way here, down this path of calm and questions. Now let's leave the surface behind. Above us, the ocean begins as a familiar blue, sunlit and busy. Waves break, fish dart, boats carve their paths. But with every metre downward, the light thins and the noise fades. The sunlit surface layer, called the epipelagic zone, reaches about 200 metres deep, and most of the life we know lives there. But below that bright band is the twilight zone, where light becomes a memory and shadows rule. Go deeper still, past 1,000 metres, and even those shadows give up their shape. This is the midnight zone, a realm of total darkness, where pressure builds and temperature falls, and yet the journey has only begun. Challenger Deep lies nearly 11,000 metres below the waves, almost 36,000 feet, in a part of the Pacific known as the Mariana Trench, east of the Philippines and south of Japan. If we were to drop Mount Everest into it, the summit would still be more than 2 kilometres underwater. Down there, the pressure is more than 1,000 times what we feel at sea level, enough to crush steel and shatter the hulls of most ships. And yet, in this place that seems designed to repel life, life persists. It's strange to think about how little we've actually seen of our own planet. We map the surfaces of Mars and the Moon in exquisite detail, but the bottom of the ocean remains largely unknown. Challenger Deep, the deepest known point of them all, has been visited by humans only a handful of times. The first was in 1960, when Swiss oceanographer Jacques Picard and US Navy Lieutenant Don Walsh descended aboard a bathyscaphe called Trieste. It was a slow, silent journey that took almost 5 hours, and when they reached the bottom, they reported seeing life, a flat fish-like creature stirring in the silt. It was a small, almost quiet discovery, but it changed the way we thought about the deep. Until then, many believed life couldn't exist in such extremes. That belief dissolved in a cloud of stirred sediment. Since then, only a few more humans have followed them down. Filmmaker James Cameron made a solo descent in 2012, a cramped 7-hour round trip to a place fewer people have visited than the Moon. More recently, explorers like Victor Vescovo have piloted deep-diving submersibles there multiple times, capturing high-definition footage and collecting samples. Each expedition brings back something new microbes, new crustaceans, new hints of how life bends the rules to survive. And every discovery reminds us how vast and mysterious Earth still is. It's easy to picture the deep sea as a kind of void, a black emptiness where nothing stirs. But that's a surface assumption. As you descend, life doesn't vanish. It changes. It becomes subtler, stranger, more ingenious. Creatures here don't chase sunlight. They make their own light through bioluminescence, signaling to each other in the dark with flashes and glows. They don't fight the pressure. Their bodies are soft, flexible, often jelly-like, designed to bend rather than break. They don't rely on abundant food. They wait for the slow rain of marine snow, tiny flakes of dead plankton, fish scales and organic matter that drift down from the surface. Or they feed on each other in complex hidden chains. Even in Challenger Deep, where food is scarce and temperatures hover just above freezing, life has found a way to adapt. Imagine yourself inside a submersible, descending through that darkness. The surface light fades to a dull grey, then a deep blue, then to nothing at all. Outside the porthole, the water grows heavier, denser, almost tactile. At around 1,000 metres, you've left behind nearly all familiar sea life. The fish here have massive eyes to capture every stray photon, or no eyes at all, relying on other senses to navigate. Some species flash patterns of light across their bodies to lure prey or confuse predators. Others drift motionless, conserving energy in a world where energy is rare. As you fall deeper, around 4,000 metres, you reach the abyssal plain, a vast expanse of soft sediment that covers much of the ocean floor. It's cold and still, but even here, life persists. Sea cucumbers, brittle stars, and strange gelatinous worms. But Challenger Deep lies far beyond this. Another 6 kilometres below, the trench plunges into a crescent-shaped scar in Earth's crust, formed where the Pacific Plate is slowly sliding beneath the Mariana Plate. It's a tectonic wound, a place where the planet folds in on itself. Down here, the pressure is over 1,086 bars, equivalent to the weight of 50 jumbo jets pressing on a single human body. It's a force that would flatten most known life instantly. Yet, life persists here too. Amphipods, small shrimp-like crustaceans, swim and scavenge in the trench. Bacteria thrive in the sediments, breaking down organic matter that drifts down from above. Some microbes even feed on chemicals released from the Earth itself, drawing energy from reactions between water and rock rather than from sunlight. The sheer adaptability of life in such a place is humbling. For decades, scientists assumed that pressure would limit the complexity of life, that membranes would rupture and proteins would unfold. But extremophils, organisms that thrive in extreme environments, have rewritten those assumptions. They build cell membranes with special molecules that stay flexible under intense pressure. Their enzymes, the tiny machines that drive life's chemistry, are shaped to function in conditions that would destroy most others. Some produce molecules called piezolites that stabilize proteins and prevent them from collapsing under stress. These adaptations don't just let them survive, they let them thrive where nothing should. Even the chemistry of this deep world is unique. The sediments of Challenger Deep are rich in organic carbon, much of it carried from the surface over thousands of years. Some comes from the slow rain of marine snow, but some comes from much farther away. Scientists have found traces of microplastics and industrial pollutants even here, carried by ocean currents and settling like dust in a forgotten room. It's a sobering reminder that even Earth's most remote places are not beyond our reach, and yet life endures amid this contamination too, incorporating human-made particles into its environment as if they were just another part of the landscape. The presence of life here also raises questions far beyond Earth. If organisms can exist under 1,000 atmospheres of pressure, without sunlight relying on chemical energy alone, then perhaps they can exist on other worlds too. Europa, one of Jupiter's moons, is thought to have a vast ocean beneath its icy crust. Enceladus, a moon of Saturn, spews water vapour and organic molecules from its subsurface sea into space. These alien oceans may be dark, cold and pressurized, but so is Challenger Deep, and life thrives there. In that sense, the trench is not just a geological feature, it's a model, a preview of what life elsewhere might look like. Despite the challenges, exploration continues. Modern submersibles are marvels of engineering built to withstand pressures that would crush a battleship. They are small, spherical, and often made of titanium or specialized synthetics, designed to balance strength with buoyancy. Robotic landers equipped with cameras, sensors, and sample collectors have also been sent to the trench, staying for hours or days to gather data. What they find often defies expectations: new species, new chemical processes, new questions about how ecosystems function in such isolation. Every descent brings the unknown a little closer, and yet, for all the technology and effort we invest in reaching Challenger Deep, much of it remains unexplored. The trench covers an area larger than many countries, and we've seen only fragments of it. Vast stretches remain untouched, waiting in the dark. Some scientists suspect that undiscovered species, perhaps even entire ecosystems, lie hidden in its folds. Others wonder if the sediments might hold clues about Earth's past, records of climate, tectonics, even ancient life. The trench is not just a physical place. It's a library written in silt and stone, and we've barely opened the first page. It's worth pausing here to think about what drives us to explore such a place. It's not easy. It's expensive, dangerous, and often yields more questions than answers. Yet, we keep returning. Perhaps it's because Challenger Deep reminds us that the unknown still exists on our own planet, that there are still frontiers left to cross. In an age when satellites map continents and algorithms predict weather, there is something profoundly humbling about a place that resists easy understanding. It's a reminder that Earth is still wilder than we think, and as we sit here, imagining the silence and darkness at the bottom of the world, it's also worth remembering that this abyss is not separate from us. The water above it cycles through our rain and rivers. The creatures below it are distant cousins to the life that thrives on land. The trench may seem alien, but it is part of the same planet, shaped by the same forces, governed by the same laws. Its existence reminds us that life is not confined to the comfortable, the familiar, or the easy. It is restless, inventive, and persistent. It goes where it shouldn't, endures what it shouldn't, and in doing so, it rewrites what is possible. The journey downward doesn't end when we reach the bottom. In many ways, that's where it truly begins. Because once we accept that life can exist here, under pressures that would crush a human body in an instant, we have to ask new questions. How does that life shape its environment? What relationships connect the microbes in the mud to the amphipods in the water column? What happens when the surface world changes, when temperatures rise, currents shift, and pollution increases? Challenger Deep is not static. It is part of a living, changing planet, and its future is tied to ours. Somewhere in that darkness, in the silence broken only by the hum of a submersible's instruments, or the faint movement of a crustacean's limbs, life continues its slow, patient work. It digests, reproduces, competes, and evolves. It writes its story in chemical reactions and genetic code, one molecule at a time. It doesn't know it lives in the deepest place on Earth. It doesn't care. It simply is. And maybe that's the lesson Challenger Deep offers us, that life doesn't need light or comfort or even certainty. It just needs a chance. As we keep sinking deeper into this story, it becomes clear that this isn't just about the animals or microbes that live at the bottom of the ocean. It's about resilience and adaptation, about how life bends without breaking. It's about how ecosystems emerge in places where nothing should survive. And it's about how, in exploring the deepest part of our planet, we discover something fundamental about ourselves, that we too are part of this stubborn, enduring story of life. The trench is not just a place, it's a mirror, showing us the extremes of what is possible and hinting that the limits we imagine may not be limits at all. So, as we leave the surface far above and settle into the darkness below, we are not just visitors, we are witnesses to a story billions of years in the making, one written not in ink or words but in adaptations and survival strategies. The deeper we go, the more it unfolds, and the more we realise how much remains unseen. And with that understanding, we keep descending, not because the abyss demands it, but because something in us longs to know what waits in the dark. The deeper you travel into the ocean, the more the surface world fades from memory. It's not just the light that disappears or the colour that drains away. It's the weight of everything above you, building layer by layer until it becomes almost unimaginable. If you were to float in the open sea a few meters below the surface, you'd feel the water pressing gently against your skin. Slip down to 10 meters, and that pressure doubles. Go to 100, and it's like having a small car resting on your shoulders. Keep going, and by the time you reach the bottom of Challenger Deep, nearly 11 kilometers down, the pressure has risen to more than 1,000 times what you feel on land. Every square centimetre of your body would have the weight of an elephant pressing against it. For most life on Earth, that's simply not survivable. And yet, somehow, in the trench, it is. The sheer magnitude of that pressure is difficult to grasp because our daily experience doesn't prepare us for it. On land, the air around us exerts about 1 atmosphere of pressure, roughly 14.7 pounds per square inch. But we don't notice it. We evolved within it, our bodies balanced against it. Water, however, is far denser than air. Every 10 meters you descend adds another atmosphere of pressure. At the bottom of Challenger Deep, you're dealing with more than 186 bars, over 15,000 pounds per square inch. It's enough to collapse steel beams and implode submarines. The fact that anything survives there at all is astonishing. The ocean's pressure is relentless because water, unlike air, doesn't compress easily. As you descend, the weight of all the water above you presses down. There's no way to escape it, no pocket of relief, no gap in the force. Every surface, every membrane, every structure must withstand it continuously. For us, built as we are for a thin film of atmosphere, this environment is instantly lethal. Human lungs would collapse, blood vessels would rupture, and even reinforced diving suits would buckle. That's why the handful of vehicles that have reached Challenger Deep are shaped like spheres. A sphere distributes pressure evenly across its surface, minimizing stress points. It's the only shape that can endure that crushing weight without folding in on itself. This unrelenting force doesn't just affect human machines. It shapes every living thing down there. Organisms that thrive in the trench have bodies unlike anything on the surface. Many lack gas-filled spaces like lungs or swim bladders, which would collapse under pressure. Instead, they rely on dense, water-filled tissues that compress little and deform smoothly. Their cell membranes are built with flexible molecules that remain functional even when squeezed. Their proteins are structured to maintain their shape despite the intense compression. Even their DNA repair mechanisms may operate differently, tuned to a world where physical forces push against them constantly. Consider the amphipods, small, shrimp-like crustaceans that live more than 10,000 meters below the surface. These creatures are barely a few centimeters long, yet they survive under pressures that would obliterate most forms of life. They do it by abandoning hard shells and gas bladders in favor of soft bodies that yield rather than resist. Their enzymes include special molecules called piezolytes, which prevent proteins from losing their shape under pressure, and their membranes contain unique lipids that stay fluid even when compressed. These adaptations aren't just survival tricks. They're the result of millions of years of evolution, fine-tuning life to flourish in conditions we would call uninhabitable. Pressure doesn't only shape the biology of the deep, it also shapes the chemistry. Water molecules themselves behave differently under such conditions. They pack closer together, forming structures that don't exist at the surface. Gases dissolve differently, and chemical reactions proceed at different rates. Minerals that are stable near the surface may transform into entirely new phases in the trench. The boundary between water and rock shifts under this weight, creating unusual chemical environments. It's in these subtle shifts that deep-sea microbes find opportunities, harvesting energy from reactions that wouldn't occur elsewhere. In a way, pressure is not just a force down here, It's part of the ecosystem itself, a fundamental element of the environment as important as temperature or light. It's remarkable how adaptable life can be. Humans spend billions of dollars building submersibles capable of surviving in the trench, and yet a single-celled microbe does it effortlessly, every second of its existence. One key reason is scale. Large, rigid structures like submarines must resist pressure because they enclose spaces filled with air. Small, soft-bodied organisms don't face the same problem. They let pressure pass through them. Their internal and external pressures balance out, eliminating the crushing force that would destroy a rigid shell. This approach, yielding instead of resisting, is counterintuitive to us, but it's one of nature's most elegant solutions. It also explains why we have found so much microbial life even in the deepest sediments of Challenger Deep. These microscopic organisms thrive in the mud, where pressure, cold, and darkness would seem to forbid life. They metabolize slowly, often feeding on chemical energy rather than sunlight. Some oxidize ammonia or methane. Others break down organic matter that has drifted from the surface over thousands of years. Their existence expands our understanding of what life can endure. If pressure isn't a barrier here, maybe it isn't elsewhere either. Maybe in the subsurface oceans of Europa or the high-pressure depths of an exoplanet's sea, similar life could exist. Pressure also affects the physical structure of the trench itself. Challenger Deep is not a simple hole in the ground. It's the result of one tectonic plate sliding beneath another, a slow-motion collision that bends the Earth's crust downward into a crescent-shaped trench. Over millions of years, sediments have accumulated at the bottom, creating a soft, shifting landscape. Earthquakes occasionally jolt the region, sending clouds of sediment billowing upward. Subtle flows of water within the trench carry nutrients and chemical compounds from one place to another. Even here, more than 10 kilometers below the surface, the planet is dynamic and alive. It's not just the geology that feels different down here. Even time itself seems to change. In a world without sunlight, the daily rhythms we take for granted vanish. There is no dawn, no dusk, no tide of light to mark the passage of hours. Life here is guided by other cycles, the slow drift of nutrients, the shifting of chemical gradients, perhaps even the vibrations of distant earthquakes. It's a reminder that the rhythms of life are not fixed. They adapt to their surroundings, even when those surroundings are as alien as the bottom of the ocean. The weight of the world above also brings with it something less poetic but equally important: gravity. It's gravity that pulls water downward, piling it atop itself and creating the immense pressure of the deep. It's gravity that drives tectonic plates to sink beneath one another, carving out trenches like Mariana. And it's gravity that ensures the water above Challenger Deep doesn't just press downward, but presses inward from all directions, turning the trench into a crucible of force. Gravity is the silent architect of this world, shaping it in ways we rarely think about. For human explorers, this weight is an engineering challenge unlike any other. Submersibles built for the trench must be small, strong, and perfectly sealed. They are often shaped like spheres because a sphere is the most efficient way to distribute pressure. Even so, the stresses are immense. Every bolt, every weld, every seam must be flawless. A single flaw can mean disaster. During the Trieste mission in 1960, Piccard and Walsh heard a loud crack on the way down. One of the outer windows had fractured under pressure. It held, but it was a stark reminder of the forces they faced. Modern vehicles use advanced materials and precision manufacturing, but the risks remain. At these depths, failure is instant and absolute. The environment's hostility also affects how we study it. Instruments must be carefully calibrated to withstand the pressure without being crushed or distorted. Cameras must be sealed in pressure-resistant housings. Even simple tasks like collecting a sample of sediment or water require specialized equipment. Yet the rewards are enormous. Samples from Challenger Deep have revealed new species of microbes and unusual chemical compounds, some with potential applications in medicine and industry. They've also provided insights into how carbon and other elements cycle through the ocean, influencing global climate. It's sobering to realise how connected this remote world is to the surface above. Tiny particles of organic matter, the remnants of plankton, fish and other organisms, drift downward over months or years, eventually settling in the trench. Some are consumed by microbes, fueling the base of the food web. Others become part of the sediment, locking away carbon for millennia. The trench is not isolated. It's part of a global system, linked by invisible threads to the surface ocean, the atmosphere, and even the land. This interconnectedness has a darker side too. Scientists have found plastic fibres, industrial chemicals, and radioactive particles in Challenger Deep. These pollutants, carried by ocean currents and atmospheric circulation, eventually sink and accumulate in the deep. It's a stark reminder that no part of Earth is untouched by human activity. Even in a place where sunlight has never shone and where only a handful of humans have ever been, our presence is felt. And life, resilient as ever, must adapt to these changes as well. Yet despite this intrusion, the deep continues. Amphipods still scavenge the seafloor, microbes still metabolize in the mud. The trench remains a functioning ecosystem, shaped by pressure but not broken by it. In many ways, the deep is a testament to life's resilience. It shows that even when the weight of the world bears down, life finds ways not just to endure but to flourish. The physical pressure is only part of the story. Psychological pressure plays a role too, though not for the creatures that live there. For humans, the idea of descending into such a place carries its own weight. The thought of kilometres of water pressing above, the darkness, the isolation, the knowledge that failure means certain death, it all adds to the sense of awe and fear. Yet that fear is also part of what drives exploration. It's the challenge, the unknown, the pull of places that resist us. The weight above is heavy, but so is our curiosity. It's worth remembering that this weight is not a sign of hostility. It's simply the nature of the deep. The pressure is not an obstacle to life here. It's the defining feature of the environment. Without it, the trench would not exist. Without it, the unique forms of life that call it home would not have evolved. Pressure is not the enemy. It is the sculptor, shaping organisms, ecosystems, and even our understanding of what life can be. Some scientists have suggested that life might not just survive under pressure but depend on it. Certain proteins, for example, may only function properly at high pressures. Some chemical reactions may proceed more efficiently. In this sense, the deep is not just a hostile place where life struggles to survive. It's a specialized environment where life thrives precisely because of the conditions. It's a reminder that what seems extreme to us is often normal to something else. The pressure also affects how sound travels. In the deep ocean, sound moves faster and farther than it does at the surface. This changes how animals communicate and how scientists study the environment. Some deep-sea creatures use low-frequency sounds to communicate across great distances. Researchers use hydrophores to listen to the sounds of the trench, from the rumble of distant earthquakes to the faint movements of marine life. The pressure shapes not just the physical and biological aspects of the environment, but the sensory landscape as well. It even influences the behaviour of sediments. Under such intense pressure, the seafloor is not static. It shifts and flows, albeit slowly. Layers of fine particles compress over time, locking in chemical signatures and microscopic fossils. These layers are records of Earth's history, of volcanic eruptions, climate shifts, even mass extinctions. By studying them, scientists can learn about the planet's past and how it has changed over millions of years. The pressure, relentless and unyielding, is both a destroyer and a preserver, and still, life endures. It bends to the pressure, adapts to it, even uses it. It becomes something new under its weight. Challenger Deep is not a barren void crushed by the ocean above. It's a living system shaped by that very force, proof that life is not limited by what seems impossible. The weight of the world above is immense, but it is also the reason this world exists at all. Without the water pressing down, there would be no trench, no unique chemistry, no specialized ecosystems. The pressure is not just a challenge, it's the defining feature that makes this realm what it is. As we continue deeper into this story, the pressure becomes less a threat and more a presence. Constant, powerful, and inescapable. It shapes everything here, from the structure of a microbe's cell membrane to the curvature of the trench itself. It reminds us that life doesn't exist in defiance of its environment, but in harmony with it, moulded by the forces around it. And as we move forward into the darker, stranger corners of Challenger Deep, that lesson will follow us. The weight of a world above is not an end. It's the beginning of everything that happens below. If you were to leave the shore behind and dive into the ocean without stopping, you'd discover that it doesn't change all at once. It transforms slowly, layer by layer, as though you're drifting through different worlds stacked on top of one another. The journey from the surface to the bottom of Challenger Deep isn't just a trip downward. It's a passage through shifting realms of light and pressure, life and silence, each more unfamiliar than the last. To understand what waits at the trench, it's worth taking this descent step by step, feeling the world change around you as the sunlight fades and the sea reveals its hidden faces. At the very top is the ocean we know, the sunlit surface layer scientists call the epipelagic zone. It extends roughly 200 meters deep and is the only part of the ocean that sees full daylight. Here, sunlight fuels photosynthesis, driving the growth of microscopic phytoplankton that form the base of the marine food web. Fish dart in and out of schools, jellyfish pulse gently through the water, seabirds dive from above, and mammals like dolphins and whales glide through this familiar brightly lit realm. Humans, too, are part of this layer. Ships cross it, swimmers splash in it, and satellites peer down through it, watching how it shifts and swirls. It's a world defined by movement and light, one where life has evolved to use every photon and every breath of oxygen. But as you leave the comfort of the surface and sink deeper, the light begins to thin. Water absorbs and scatters sunlight, and by the time you reach about 50 meters, the bright reds and oranges vanish first, replaced by muted blues and greens. At 100 meters, the world dims further, the colors draining into shades of indigo. By 200 meters, where the epipelagic zone ends, only a faint ghostly blue remains, and even that fades quickly beyond. Here begins the mesopelagic zone, often called the twilight zone. It stretches from 200 to 1,000 meters deep and is a place of perpetual dusk. Sunlight still filters through, but it's too weak to support photosynthesis. Plants cannot live here. The energy that sustains life must come from above, drifting down as tiny flakes of organic matter or in the form of prey that migrate downward. In this dim layer, life changes its strategy. Many creatures migrate vertically, rising toward the surface at night to feed and sinking back into the safety of darkness by day. Lanternfish, which make up a huge portion of the world's fish biomass, follow this daily rhythm, moving hundreds of meters up and down in one of the largest migrations on Earth. A movement not of continents, but of water columns. Other creatures embrace the gloom by producing their own light. Bioluminescence becomes more common here, a biological trick that serves many purposes: communication, camouflage, hunting, and defense. Tiny plankton flash to startle predators. Predators use glowing lures to attract prey. Some fish glow on their undersides, matching the faint light from above so that they vanish against the surface if viewed from below. It's a world that has learned to write with light in the absence of sunlight. As you descend past 1,000 meters, even that faint glow from the sun disappears. You have entered the pelagic zone, the midnight zone. No sunlight reaches here at all. The water is cold, often near freezing, and the pressure is immense, hundreds of times greater than at the surface. The darkness is absolute, yet it is not empty. Life persists here too, though it is stranger and scarcer than in the layers above. Many creatures here are slow-moving, conserving energy in a place where food is rare. Some are giants, like the colossal squid, whose eyes are among the largest in the animal kingdom, evolved to detect the faintest glimmer of movement in the dark. Others are tiny but luminous, using bioluminescence to lure prey or find mates in the blackness. Here, the rules of life shift. Vision becomes less important. Speed matters less than patience. Survival is a waiting game, and those who endure do so with exquisite efficiency. The Midnight Zone extends to around 4,000 meters, and below it lies the abyssopelagic zone, the Abyss. From 4,000 to about 6,000 meters, the ocean floor spreads out into vast plains of soft sediment. These abyssal plains cover more than half of Earth's surface and are among the most stable environments on the planet. They are cold, dark, and nearly motionless, shaped by the slow rain of organic material drifting down from above. Much of that rain is consumed before it arrives, so food is scarce. Yet the animals here, sea cucumbers, brittle stars, polychaete worms, survive by consuming what little arrives. They move slowly, conserving energy, their lives measured not in hours or days but in years and decades. Descending through these layers is like moving through different worlds, not just because the light changes, but because the very nature of life and environment transforms with it. Temperature drops steadily, from the warmth of the surface to near freezing in the deep. Salinity stabilizes, water becomes denser. Oxygen levels rise and fall depending on depth and location. The deeper you go, the more uniform the environment becomes, a vast, dark, stable world that has changed little in millions of years. And yet it is full of subtle gradients and invisible boundaries, each shaping life in its own way. Below the abyss lies the Hadal Zone, named after Hades, the Greek underworld. This is the realm of the ocean trenches, the deepest parts of the seafloor, stretching from 6,000 meters down to the deepest points like Challenger Deep. Less than 1% of the ocean floor lies at these depths, and it is the least explored region on Earth. The Hadal Zone is not a continuous band like the zones above. It exists in scattered trenches, deep scars carved into the seafloor by the slow grinding of tectonic plates. These trenches are narrow and steep-sided, with walls that plunge downward like cliffs and floors covered in fine sediment. They are shaped by immense geological forces, subduction zones where one plate slides beneath another, and they are home to conditions unlike anywhere else on Earth. As you descend into a trench like the Mariana, the experience changes again. The water pressure, already immense, climbs higher still. Temperatures remain just above freezing. No sunlight has ever touched this place, and no seasonal changes ripple through it. It is a world of perpetual night and near-total stillness. Even sound changes here. Low-frequency vibrations travel far, while higher-pitched sounds are quickly absorbed. The silence feels physical, pressing in from all sides. And yet, even here, life exists. Amphipods scurry across the sediment, scavenging for food. Holothurians, deep-sea sea cucumbers, inch their way along the sea floor, consuming organic particles. Xenophyophoras, giant single-celled organisms, build intricate structures from sediment grains. Microbes flourish in the mud, metabolizing chemicals and breaking down organic matter. These organisms are often small and slow-growing, adapted to a life where food arrives in tiny, unpredictable bursts. Some feed on the rain of detritus from above. Others rely on chemical energy from reactions between seawater and the rocks below. It is a sparse, delicate ecosystem, but it is alive. The descent through these layers is not just a physical journey, it's also a journey through Earth's history. Each layer tells a story about how life adapts to its environment. At the surface, sunlight and photosynthesis dominate. In the twilight zone, migration and bioluminescence become key. In the midnight zone, patience and sensory adaptation rule. In the abyss, life slows to a crawl, surviving on the margins, and in the Hadal trenches, life bends itself around the extremes, finding ways to exist where almost nothing else can. It's a story of gradual change, of evolution finding solutions at every depth. It's also a story of connection. The ocean is not a series of isolated layers, but a continuum. Water moves between them, carrying nutrients, heat, and organisms. Marine snow falls from the surface to the abyss, linking the productivity of the sunlit ocean to the darkness below. Migrating animals cross boundaries daily, blurring the lines between zones. Even tectonic activity in the deep affects the surface, generating tsunamis or shaping coastlines. The descent through the ocean is not a trip into isolation, but a journey through a connected, dynamic system. For humans, experiencing this descent firsthand is rare. Most of what we know about the deep comes from instruments and remotely operated vehicles. Cameras capture images of glowing jellyfish in the twilight zone. Sensors record temperature, pressure, and chemical composition. Landers collect samples from the seafloor. Each piece of data is a small glimpse into a vast hidden world. Even so, the idea of travelling through these layers captures the imagination. It's a journey from the familiar to the alien, from light to darkness, from abundance to scarcity. It's a reminder of how diverse and resilient life can be. The way light changes on this descent is especially striking. Light defines our experience of the world. It shapes how we see, how we live, how we understand time and space. As it fades, the world transforms. Shadows lengthen, colours vanish, and eventually, vision itself becomes useless. In the deep ocean, many animals abandon eyes altogether. Others evolve eyes that are sensitive to bioluminescence rather than sunlight. Some rely on pressure waves or chemical signals to sense their environment. The absence of light doesn't mean the absence of information. It just means information comes in different forms. Bioluminescence becomes more than a curiosity here. It becomes a language. Some deep-sea animals use it to communicate, flashing patterns to attract mates or coordinate group behaviour. Others use it as camouflage, matching the faint light from above to become invisible. Predators use glowing lures to attract prey, mimicking the flicker of smaller organisms. Even microbes can produce light, creating faint glows in the water or on the seafloor. This living light is chemical, generated by reactions involving molecules like luciferin and enzymes like luciferase. It's a reminder that light in the ocean is not just something that comes from above, it's something life creates for itself. The fading of sunlight also changes the way energy flows. In the surface ocean, energy starts with the sun, captured by phytoplankton and passed up the food web. In the deep ocean, energy is imported. It arrives as marine snow, tiny particles of organic matter that drift downward, sometimes taking weeks or months to reach the bottom. It arrives as larger carcasses, like the occasional whale fall, which can support entire ecosystems for decades. And in some places, it arrives from the Earth itself, as chemical energy from hydrothermal vents or serpentinization reactions in the crust. These energy sources shape the communities that live there, determining who thrives and who struggles. Descending through the ocean also reveals how pressure and darkness shape behaviour. Many deep-sea animals are ambush predators, conserving energy by lying in wait rather than chasing prey. Others are detritivores, sifting through sediment for tiny particles of food. Some are filter feeders, capturing organic matter from the water as it drifts by. Reproduction is often slow and infrequent, with many species producing few offspring that grow slowly over many years. Life here is about efficiency, using as little energy as possible to survive in an environment where resources are scarce. This slow pace extends to geological processes too. Sedimentation in the deep ocean is incredibly gradual. It can take thousands of years for a single centimetre of sediment to accumulate. Yet those sediments preserve a record of Earth's history. Layers of volcanic ash, microfossils and chemical signatures that tell stories of past climates, mass extinctions, and shifting continents. By studying cores from the deep sea floor, scientists can reconstruct events that shaped life on Earth millions of years ago. In this way, the deep ocean is not just a biological frontier, it's a geological archive, a library of Earth's memory. As you imagine yourself sinking deeper into the trench, the descent becomes more than a journey through physical layers. It becomes a journey inward, into the nature of life itself. It shows us that life is not bound to one set of conditions. It can flourish in sunlight or darkness, in warmth or cold, in abundance or scarcity. It can build forests on land, reefs in shallow seas, and microbial mats in the Hadal depths. The deeper you go, the more you see that life is not fragile. It is endlessly adaptable, endlessly inventive. It's tempting to think of Challenger Deep as the endpoint of this journey, the ultimate destination. But it's more accurate to think of it as part of a continuum. The same forces that shape the surface ocean shape the trench. The same water that laps at the shore presses down on the sea floor. The same nutrients that feed plankton in the sunlit zone eventually sink to feed microbes in the mud. The trench is not separate from the rest of the ocean. It is part of it, connected by water, chemistry, and life. And just as the trench is connected to the ocean is connected to us. The water that fills the trench evaporates into clouds, falls as rain, flows into rivers, and returns to the sea. The oxygen produced by plankton in the surface ocean fills our lungs. The carbon stored in deep-sea sediment shapes our climate. Even the pressure and darkness of Challenger Deep influence the world above, driving circulation patterns and chemical cycles that affect life everywhere. The descent through the ocean is not just a physical journey. It's a reminder of the deep connections that bind Earth together. The deeper you go, the more those connections matter. The organisms that live in the Hadal zone are shaped by what happens at the surface, just as the surface is shaped by what happens below. A bloom of plankton in the sunlit zone can eventually become food for amphipods in the trench. A tectonic shift in the deep can send waves racing across the ocean, reshaping coastlines. Even human actions, burning fossil fuels, releasing pollutants, warming the climate, reach into the depths. Plastic fibres and industrial chemicals have been found in Challenger Deep, carried down by currents and trapped in sediments. The descent through the ocean is not a journey into isolation. It's a journey into the heart of a single interconnected system. And so, as we continue downward, passing from light into darkness, from warmth into cold, from abundance into scarcity, we're not just exploring a remote part of the world. We're exploring the conditions that shape life itself. Each layer of the ocean is a different expression of the same planet, a different solution to the same challenges. Together, they form a continuous gradient from the familiar to the alien, from the world we know to the world we're only beginning to understand. And somewhere, far below, in the stillness and pressure of Challenger Deep, that gradient reaches its most extreme expression, a place where light has never shone, where pressure crushes steel, and where life nevertheless endures. The descent is far from over. The deeper we go, the stranger it becomes, and the more it teaches us about resilience, adaptation, and connection. What waits in the blackness below is not just a collection of strange creatures and exotic chemistry. It is a story about life's capacity to find a way, no matter how dark, how cold, or how heavy the world above becomes. The deeper the water grows and the heavier the world presses down, the more it seems as if nothing could possibly live there. Every instinct tells us that such a place should be empty, that life depends on light and warmth and gentle surroundings. And yet, the ocean refuses to obey those instincts. Challenger, Deep, a place where sunlight has never shone, where the pressure would crush steel, where temperatures hover near freezing, is alive. It's not teeming with the familiar shapes we know from coral reefs or coastal waters, but it is far from lifeless. Life here has learned to endure the unimaginable. It has not merely survived the extremes, it has built a home in them. This idea that life persists against all odds is one of the most profound lessons the deep ocean offers. For a long time, scientists believed that the deepest parts of the sea were barren. Before the first expeditions into the trench, many argued that no organism could withstand such crushing pressure or survive in total darkness without sunlight. It was a logical assumption, based on the environments where life is most abundant. But logic, it turns out, underestimates life. When the bathyscaphe Trieste descended into Challenger Deep in 1960 and returned with evidence of living organisms, that assumption crumbled. Since then, every exploration has reinforced the same truth. Where there is water, there is a way. Life in the trench is different not because it wants to be, but because it must be. It cannot rely on the strategies that work at the surface. Photosynthesis, the process that powers most life on Earth, is impossible here. There is no light to fuel it. The creatures that live at these depths rely instead on what drifts down from above or on chemical reactions that have nothing to do with sunlight. Marine snow, a steady rain of organic particles, dead plankton, fecal pellets, and other detritus, provides a slow but constant source of food. Occasionally, larger meals arrive. A dead fish, a fallen squid, even a whale carcass sinking to the sea floor. These events can sustain entire communities for years. But life here has learned not to depend on abundance. It thrives on scarcity, stretching every resource as far as it will go. One of the most striking examples of adaptation in Challenger Deep is the amphipod. These small, shrimp-like crustaceans are among the most common animals in the Hadal zone. They are scavengers, feeding on whatever organic material reaches the trench. To survive the crushing pressure, their bodies are soft and flexible, with few hard parts that could crack or collapse. They produce special molecules called piezolites that help protect their proteins from pressure-induced damage. These molecules prevent enzymes from unfolding and keep membranes functioning even under more than 1,000 atmospheres. Amphipods also have remarkable digestive systems that allow them to extract maximum nutrition from even the most meagre scraps. They are, in many ways, the perfect trench survivors, small, efficient, and endlessly adaptable. Other animals have evolved even stranger strategies. Holothurians, or sea cucumbers, creep slowly across the sea floor, ingesting sediment and extracting organic matter from it. They move with deliberate slowness, conserving energy in a place where food is rare. Some species of worms burrow into the mud, feeding on the tiny particles trapped there. Xenophytophores, giant single-celled organisms that can grow up to 10 centimeters across, build elaborate structures from sediment grains, creating miniature habitats for other organisms. These creatures are not flashy, they are not fast or fierce, but they are superbly suited to their environment. Microbial life in Challenger Deep is even more remarkable. Bacteria and archaea thrive in the sediments, metabolizing compounds like ammonia, methane, and hydrogen sulfide. Some of these microbes are chemolitho autotrophs, meaning they obtain energy by oxidizing inorganic molecules rather than consuming organic matter. They are, in effect, independent of the surface world, drawing power from the chemistry of the Earth itself. Others form symbiotic relationships with larger organisms, living inside their hosts and providing them with nutrients. These microbial communities form the foundation of the trench ecosystem, recycling nutrients and sustaining higher forms of life. Without them, the fragile balance of the deep would collapse. The adaptations that allow life to persist here are as diverse as the organisms themselves. Cell membranes, for example, must remain fluid and functional under immense pressure. Deep-sea organisms achieve this by incorporating more unsaturated fatty acids into their membranes, which prevent them from becoming too rigid. Proteins must maintain their three-dimensional structures despite the crushing force of the water. So many deep-sea organisms produce pressure-stabilizing molecules like trimethylamine N oxide, TMAO. The concentration of TMAO increases with depth, a clear sign of how essential it is to life under pressure. DNA repair mechanisms are often enhanced, protecting cells from damage caused by high-pressure environments. Even basic cellular processes like respiration and metabolism are adjusted to function optimally under conditions that would cripple surface-dwelling species. Life's persistence here is not just a biological curiosity. It has profound implications for our understanding of life itself. If organisms can thrive in Challenger Deep, they might be able to survive in other extreme environments as well. Scientists studying extremophiles, organisms that live in extreme conditions, have drawn parallels between the Hadal Zone and extraterrestrial environments. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, are believed to have subsurface oceans beneath their frozen crusts. These oceans are dark, cold, and under high pressure, much like Challenger Deep. If life can exist here, why not there? The same principles that sustain microbes in the trench might support alien ecosystems beneath the ice. This idea is more than speculation. Microbes from the deep ocean have already shown an astonishing ability to tolerate conditions similar to those expected on icy moons. Some can metabolize using chemical energy alone. Others can survive intense radiation or extreme temperature shifts. These traits suggest that life is not a delicate phenomenon, limited to a narrow range of conditions. It is robust and adaptable, capable of thriving wherever it can find energy and stability. The trench, in this sense, is not just a remote part of Earth. It's a model for life's potential across the universe. The resilience of life in Challenger Deep also challenges our assumptions about what life needs. We often think of sunlight as the foundation of all ecosystems, but the trench shows that this is not true. Life there relies on detritus, on chemical energy, and on slow, patient cycles that unfold over centuries. Some microbes in the sediments reproduce so slowly that their generations span decades, yet they persist, generation after generation, maintaining a living presence in the most forbidding environment on Earth. This persistence forces us to rethink what we mean by habitable. If life can exist in the pitch-black high-pressure mud of the trench, the universe may be far more habitable than we once believed. Even the behavior of deep-sea organisms reflects their adaptation to scarcity and pressure. Many trench-dwelling animals are opportunistic feeders, consuming whatever they encounter rather than specializing in a single food source. Some can go long periods without eating, slowing their metabolism to a crawl when food is scarce. Reproduction too is shaped by the environment. Some species produce fewer offspring but invest more resources in each, increasing the chances of survival. Others release vast numbers of eggs or larvae into the water, gambling that a few will find suitable conditions. These strategies reflect the unpredictability of life in the trench, a world where food might arrive in a steady trickle or in sudden rare windfalls. The structure of deep-sea ecosystems is shaped by this unpredictability. Rather than large, stable populations, the trench is home to small, scattered communities. Many species have wide distributions, spread across different trenches and deep-sea habitats. Others are endemic, found only in a single trench or even a specific part of it. This patchiness makes the Hadal Zone one of the most complex and least understood ecosystems on Earth. Studying it is a challenge not just because of the physical difficulties of exploration, but because the systems themselves are so finely tuned and dynamic. What we do know suggests that life in the trench is not isolated. It is connected to the broader ocean in ways that are subtle but significant. Organic matter from surface waters eventually sinks to the depths, carrying with it carbon and nutrients. Ocean currents transport water masses from one region to another, linking distant parts of the deep. Migrating animals carry energy and matter between layers. Even seismic activity on the seafloor can shape ecosystems by stirring sediments and releasing nutrients. the trench is not a separate world. It is part of a continuum that extends from the surface to the abyss. This connection is a double-edged sword. While it sustains life in the trench, it also carries the imprint of human activity. Microplastics, industrial chemicals and radioactive particles have all been found in Challenger Deep. These pollutants arrive from the surface, carried by currents and sinking particles, and they accumulate in the sediments where microbes and invertebrates live. Some organisms even incorporate microplastics into their bodies, a sign of how deeply human influence has penetrated the planet. And yet, even in the face of this intrusion, life continues. Microbes metabolize pollutants. Amphipods scavenge among plastic fibers. The ecosystem endures, adapting once again to conditions it did not create. The story of life in Challenger Deep is, at its heart, a story of adaptation. Every feature of every organism, from the composition of its cell membranes to the way it reproduces, is shaped by the demands of the environment. Pressure, darkness, scarcity, and cold are not just challenges. They are the defining features of the trench, and life has woven them into its very fabric. The organisms here are not merely surviving despite the conditions, they are thriving because of them. They are specialists in the extreme, masters of a world that would kill most other life in an instant. Even the pace of life here reflects this adaptation. Growth is slow, reproduction is infrequent. Ecosystems change gradually, often over centuries, but this slowness is not a weakness, it is a strategy. In a place where energy is scarce and conditions are stable over long timescales, rapid change would be wasteful. Instead, life invests in stability, building systems that endure over time. It's a lesson that contrasts sharply with the surface world, where change is constant and speed is often the key to survival. In the trench, patience is the currency of life. This patience extends beyond biology to the geological and chemical processes that sustain the ecosystem. Sediments accumulate slowly, trapping organic carbon and nutrients over millennia. Chemical gradients shift gradually, shaping microbial communities. Even tectonic activity unfolds over vast timescales, altering the shape of the trench and the distribution of habitats. Life here is attuned to these slow rhythms, adapting to changes that unfold over centuries or even longer. It is a world where time moves differently, not because the clocks run slower, but because the processes that shape it do. The resilience and adaptability of life in Challenger Deep remind us that life is not a fragile anomaly. It is a fundamental property of Earth. Wherever conditions allow, and sometimes even when they seem not to, life emerges. It does not require ideal circumstances. It requires opportunity. And when opportunity presents itself, life will find a way. This truth is as evident in the microbes of the trench as it is in the forests on land or the coral reefs in shallow seas. Life is not defined by its environment. It defines its environment, shaping it and being shaped by it in return. The trench shows us too that survival is not about resisting the environment, but about embracing it. The organisms here do not fight the pressure, they accommodate it. They do not flee the darkness, they evolve to live without light. They do not lament scarcity, they adapt to make the most of what is available. In doing so, they reveal a broader truth about life on Earth. Resilience is not the absence of challenge, but the ability to turn challenge into opportunity. And while the creatures of Challenger Deep are far removed from us, their story is not separate from ours. They are part of the same evolutionary tapestry, shaped by the same forces that shaped us. Their existence expands the boundaries of what we consider possible, reminding us that life is far more versatile and creative than we often assume, and in that reminder lies something deeply hopeful. If life can flourish under 11 kilometers of water, in darkness and crushing pressure, then perhaps it can flourish in other unlikely places, beneath the ice of distant moons, in the subsurface oceans of exoplanets, or even in the deep interior of our own planet. The persistence of life in the trench, also forces us to confront our responsibilities. The pollutants that have reached Challenger Deep did not arrive there by accident. They are the result of human choices, carried by the same currents that deliver nutrients and life. If even this remote, extreme environment is not beyond our reach, then nowhere is. Protecting these ecosystems means recognizing their value, not just as scientific curiosities, but as vital parts of Earth's biosphere. They play roles in carbon cycling, nutrient storage, and even climate regulation. They are part of the planet's balance, and their health is tied to ours. As we continue deeper into this hidden world, the lesson remains clear. Life is not limited by the boundaries we imagine. It is not confined to the comfortable, the familiar, or the visible. It exists in boiling vents and frozen deserts, in radioactive waste and polar ice. It exists 11 kilometers beneath the sea, in darkness and silence and crushing weight. It exists wherever it can, and sometimes where we think it cannot. The trench is proof of that. It is a place where life has written itself into the most unlikely of settings, where it has bent physics and chemistry to its will, where it has thrived not by resisting the environment but by becoming part of it. And the deeper we look, the more we see that this is not an exception. It is the rule. Life, by its nature, finds a way. It always has, and it always will. The deeper you look into the trench, the clearer it becomes that survival here isn't a matter of chance. It's the result of intricate design, not in the sense of deliberate planning, but in the way evolution shapes life into forms that are perfectly suited to their environment. Challenger Deep is not a place where life simply endures. It is a place where life has engineered itself, piece by piece, to thrive under pressures and conditions that would destroy almost anything else. Every organism here is an architect of its own survival, built by millions of years of adaptation into a masterpiece of resilience. Survival in such an environment starts with the most basic building block of life, the cell. At the surface, cells are under little physical stress. Their membranes, the thin, flexible layers that separate the inside of the cell from the outside world, are stable and fluid. Proteins fold into precise shapes, enzymes catalyze reactions with ease, and DNA remains stable within the nucleus. None of that is guaranteed in Challenger Deep. At pressures exceeding 1,000 atmospheres, membranes can become rigid and brittle. Proteins can unfold or lose their function. Enzymes that work perfectly well at the surface may become useless in the trench. Life here must solve these problems at the molecular level, redesigning itself so that its most fundamental processes continue to function. One of the most elegant solutions is the production of molecules called piezolites. These small organic compounds, found in many deep-sea organisms, help stabilize proteins and membranes under extreme pressure. One of the most common is trimethylamine N-oxide, or TMAO. At the surface, TMAO plays a minor role in helping fish maintain the balance of salts and water in their bodies. In the deep sea, its role becomes far more important. TMAO counteracts the destabilizing effects of pressure on proteins, allowing them to maintain their shape and function. The deeper an organism lives, the more TMAO it tends to produce. This correlation is so consistent that scientists can estimate the depth at which a fish lives simply by measuring the concentration of TMAO in its tissues. It's a chemical signature of adaptation, a molecular blueprint for survival. Cell membranes also undergo fundamental changes. Under high pressure, the lipid molecules that make up a membrane tend to pack more tightly, which can make the membrane too rigid for proper function. To counteract this, deep-sea organisms incorporate more unsaturated fatty acids into their membranes. These molecules have kinks in their structure that prevent tight packing, keeping the membrane fluid even under immense pressure. This fluidity is essential for processes like nutrient transport, waste removal, and cell signaling. Without it, cells would quickly die. The composition of these membranes is not random. It's finely tuned to the pressure, temperature, and chemical conditions of the trench. Even the machinery that copies and repairs DNA is shaped by the deep. High pressure can increase the likelihood of DNA damage and alter the structure of nucleic acids. In response, many deep-sea organisms have enhanced DNA repair mechanisms. Some produce specialized enzymes that detect and correct damage more efficiently. Others rely on protective proteins that shield DNA from pressure-induced distortion. These adaptations ensure that genetic information remains stable over generations, allowing life to persist in an environment that constantly tests its limits. The architecture of survival is not limited to the microscopic. It extends to the shapes and structures of entire organisms. Many animals in the Hadal zone have soft, gelatinous bodies that can compress without breaking. Bones and shells, common in surface animals, are rare here because they would fracture under pressure. Amphipods, for example, have flexible exoskeletons that deform under stress rather than shattering. Fish that live at great depths often lack swim bladders, gas-filled organs that help control buoyancy, because gas is highly compressible and would collapse under pressure. Instead, they rely on oil-filled sacs, low-density tissues, or special proteins to maintain buoyancy without risking structural failure. Some of the most extraordinary examples of adaptation are found in deep-sea snailfish. These small, pale fish have been recorded at depths beyond 8,000 meters, making them some of the deepest living vertebrates known. Their bodies are soft and flabby, their bones reduced, and their muscles adapted to function in cold, high-pressure water. They lack swim bladders and instead achieve buoyancy through the composition of their tissues. Their enzymes are tuned to operate at low temperatures and high pressures, and their membranes remain fluid in conditions that would freeze or crush those of most other fish. Every part of their anatomy is a response to the demands of the trench. They are not visitors here. They are native inhabitants sculpted by evolution into perfect denizens of the deep. Behavior, too, becomes part of the survival strategy. In an environment where energy is scarce, wasting it can be fatal. Many trench-dwelling organisms move slowly and deliberately, conserving energy whenever possible. Some are ambush predators, waiting motionless for prey to come close rather than chasing it. Others feed opportunistically, consuming whatever they encounter rather than specializing in a single food source. Reproductive strategies reflect the same principle. Some species produce few, well-developed offspring that have a higher chance of survival. Others release vast numbers of eggs or larvae, relying on probability rather than investment. Each approach is an adaptation to the unpredictable nature of life in the deep. The architecture of survival is not just biological, it is also ecological. Every organism in Challenger Deep is part of a network, connected to others in ways that sustain the system as a whole. Microbes break down organic matter, releasing nutrients that feed larger organisms. Amphipods scavenge on dead material, recycling carbon and energy. Predators keep populations in balance. Even the sediments themselves play a role, trapping and releasing nutrients over long timescales. This web of interactions is delicate but robust, able to persist despite the scarcity and isolation of the trench. It is a reminder that survival is not only about individual adaptation, but about the collective balance of an ecosystem. Some organisms have taken adaptation even further, forming partnerships that enhance their survival. Symbiosis, the close association between different species, is common in the deep ocean. Certain worms host chemosynthetic bacteria in their tissues, providing them with a safe environment in exchange for nutrients. Some amphipods harbour microbes in their guts that help digest otherwise indigestible material. These relationships expand the possibilities for life, allowing organisms to exploit resources they could not use alone. In a world where every resource is precious, cooperation can be as powerful as competition. Even the microbes in Challenger Deep are architects of survival on a planetary scale. They play crucial roles in the cycling of carbon, nitrogen, and other elements, influencing processes that extend far beyond the trench. Some microbes convert inorganic nitrogen into forms that other organisms can use. Others break down complex organic molecules, returning carbon to the ecosystem. These processes not only sustain life in the trench, but also affect the chemistry of the global ocean. In this way, the adaptations that allow microbes to survive here also help regulate Earth's broader systems. The trench's microbial life has revealed another fascinating adaptation: the ability to use alternative sources of energy. Without sunlight, photosynthesis is impossible, but some microbes use chemosynthesis, drawing energy from chemical reactions. Others exploit redox gradients, differences in the availability of electrons between various compounds, to fuel their metabolism. Some even use hydrogen or methane as energy sources. These strategies demonstrate that life does not require sunlight or organic carbon to thrive. It only requires a way to harness energy from its surroundings. This flexibility is one reason scientists believe similar life could exist elsewhere in the universe, in places where sunlight never reaches. The physical structures that allow survival in the trench are as remarkable as the biological ones. Deep-sea animals often have bodies with minimal calcification, reducing the risk of brittle failure under pressure. Many have reduced or absent swim bladders, relying instead on lipid-rich tissues that compress less under pressure. Some produce antifreeze proteins to prevent ice crystal formation in near-freezing water. Even sensory systems are adapted. Eyes, if present, are often large and highly sensitive, tuned to detect faint glimmers of bioluminescence. Some animals rely on non-visual senses entirely, detecting vibrations or chemical signals in the water. Each feature is a piece of the puzzle, a response to the challenges of life in the Hadal zone. It is worth noting that these adaptations do not arise quickly. They are the result of countless generations of natural selection, each one fine-tuning life's architecture to better match the demands of the environment. Evolution in the deep sea is a slow, patient process, shaped by stability rather than rapid change. The conditions of the trench, darkness, cold, pressure, scarcity, have remained relatively constant for millions of years, giving evolution the time and opportunity to sculpt life into extraordinary forms. This stability is one reason the adaptations here are so specialized and effective. They are the result of a long, unbroken dialogue between life and environment. Human exploration of the trench has also revealed how sensitive these adaptations can be. Organisms that thrive under immense pressure often struggle to survive when brought to the surface. The sudden drop in pressure can cause their cells to rupture, their proteins to denature, and their membranes to fail. Scientists studying deep-sea life often must recreate trench-like conditions in the laboratory, using pressure vessels to keep samples alive. These challenges highlight just how finely tuned life is to its environment, and how different that environment is from the world we know. The specialized adaptations of trench life also raise intriguing questions about the limits of biology. How deep can life go? How much pressure can it endure? How slow can metabolism become and still sustain life? The answers are not yet clear. Life has been found in trenches deeper than 10,000 meters and in boreholes drilled into the crust where pressure exceeds that of Challenger Deep. Some microbes have been shown to survive pressures far beyond what exists naturally on Earth. These findings suggest that the limits of life are broader than we once believed, and that Challenger Deep may not represent the endpoint but merely one point along a vast continuum. The architecture of survival here is not just a response to the present conditions, it is also shaped by history. The organisms in Challenger Deep are descended from ancestors that once lived in shallower waters. Over millions of years, as tectonic forces deepened the trench and conditions changed, life followed. Each step downward required new adaptations, new solutions, new architectures. What we see today is the culmination of that journey, a community of organisms perfectly matched to their environment because they have been evolving with it for millions of years. This coevolution of life and environment is part of what makes the trench such a fascinating place to study. It is not just a snapshot of life in the present, but a record of life's ongoing dialogue with the planet. It's easy to think of Challenger Deep as static, but even here, change is constant. though it unfolds on timescales far longer than we're used to. Sediments accumulate, tectonic plates shift, currents alter the flow of water and nutrients. Life responds to these changes, adjusting its architecture as needed. Some adaptations may become obsolete, replaced by new ones. Others may persist, unchanged for millions of years. This slow, continuous adaptation is part of what makes life in the trench so resilient. It is not brittle or fixed. It is flexible, able to bend and evolve with the world around it. Human technology, too, must become an architect of survival if it is to explore this world. Submersibles must be built to withstand crushing pressure, using spherical designs and materials like titanium or synthetic ceramics. Instruments must be sealed against the immense force of the water. Sampling equipment must function in the cold and darkness without contaminating delicate ecosystems. Even communication is a challenge. Radio waves cannot penetrate water, so submersibles must rely on acoustic signals. These engineering solutions mirror the biological ones in their ingenuity. They are our version of piezolites and flexible membranes, our way of adapting to a world that is fundamentally hostile to us. Yet even our most advanced machines are temporary visitors here. Life, by contrast, is permanent. It does not resist the environment or fight against it. It becomes part of it, using its challenges as tools rather than obstacles. The organisms of Challenger Deep are not just surviving despite the pressure, darkness and scarcity. They are thriving because of them. Each adaptation, from the molecular to the ecological, is a solution carved by evolution's patient hand. Each is a piece of the architecture that allows life to exist where it should not. In the end, that is perhaps the most remarkable thing about Challenger Deep. It is not a void, not a place where life hangs on by a thread. It is a vibrant, functioning ecosystem, shaped by forces we once thought would extinguish life, but that instead have given rise to new forms of it. The pressure that would crush a submarine is the same pressure that keeps membranes stable. The darkness that seems lifeless is the stage for a symphony of bioluminescence. The scarcity that appears limiting is the catalyst for efficiency and cooperation. The very challenges that make the trench seem uninhabitable are the same ones that make it such a fascinating and diverse habitat. As we continue deeper into this world, it becomes clear that the story of Challenger Deep is not just about survival. It is about mastery. Life here has not only endured the most extreme conditions on Earth, it has turned them into opportunities. It has built itself from the ground up to fit this environment perfectly, shaping its molecules, its bodies, its behaviours, and its relationships to match the demands of the deep. It is not an outsider here. It is the architect, the engineer, the designer of its own existence. And in that quiet, crushing darkness, life reminds us of one of its oldest truths. Adaptation is not just a way to survive, it is a way to thrive. The deeper you descend into the trench, the more the darkness becomes something physical, not just the absence of light, but a presence in itself, heavy, total, unbroken. It swallows everything, erasing shapes and colours, muting movement, stretching distance into something immeasurable. And yet, within that absolute blackness, life moves, it glides, it pulses, it flickers. It hides in the silt, drifts in the current, or hovers motionless for hours, waiting for the right moment to act. The creatures that inhabit Challenger Deep are unlike anything most of us have ever seen. They are not built for our world. They are the ghosts of the black, perfectly shaped for a realm where light has never shone and sound travels differently, where the weight of an entire ocean presses from all sides. What strikes you first about these beings is how strange and otherworldly they appear. They are not the sleek, streamlined swimmers of the surface or the colourful, flamboyant creatures of coral reefs. They are pale, often translucent, their bodies soft and gelatinous, their forms reduced to only what is necessary. Here, extravagance is a luxury no organism can afford. Everything about them, their size, their shape, their behaviour, is dictated by the realities of the deep. They are efficient, they are subtle, and above all, they are adapted to endure. The snailfish is one of the most emblematic inhabitants of the Hadal depths. At first glance, it is an unremarkable animal, small, ghostly white, with a soft body and delicate fins, but its simplicity hides a set of extraordinary adaptations. Unlike most fish, snailfish lack swim bladders, which would collapse under intense pressure. Their bones are reduced and flexible, preventing fractures. Their muscles are designed to function in cold, high-pressure water, and their enzymes are tuned to the unique chemistry of the trench. They glide slowly through the darkness, feeding on amphipods and other small invertebrates. They are fragile in appearance, but they are among the most pressure-resistant vertebrates on Earth, living at depths that would crush a nuclear submarine. Amphipods themselves are among the most numerous and vital inhabitants of Challenger Deep. These small, shrimp-like crustaceans are scavengers, feeding on marine snow and any organic material that reaches the trench. They are opportunists, consuming everything from microscopic detritus to the carcasses of larger animals that drift down from above. Amphipods are also key players in the ecosystem, recycling nutrients and providing food for larger predators like snailfish. Their bodies are soft and flexible, and they produce pezolites like TMAO to protect their proteins from pressure-induced damage. Some amphipods are transparent, their internal organs visible through their skin, while others are tinted pink or orange from the pigments in their diet. They are small, often just a few centimetres long, but in the Hadal world they are giants of survival. Beyond these more visible creatures lies a realm of life so small and so alien that it is easy to overlook. The sediments of Challenger Deep teem with microbes, bacteria and archaea that live in the mud, metabolizing compounds like methane, ammonia, and hydrogen sulfide. Some of these microbes form mats or biofilms, thin layers of living cells that coat the sea floor. Others burrow into the sediment, living in the spaces between grains of sand. They form the base of the trench's food web, breaking down organic matter and releasing nutrients that sustain larger organisms. Their metabolism is slow, often taking years to complete processes that happen in minutes on the surface. But in the deep, time itself seems to stretch, and slow is not a disadvantage. It is a way of life. Some of these microbes belong to groups that were unknown until recently, discovered only through genetic sequencing of sediment samples. Many have no close relatives in known ecosystems, suggesting that the Hadal zone is home to entire branches of life's tree that remain unexplored. Some of these microbes use energy sources that are rare or absent elsewhere. They oxidize hydrogen produced by the interaction of seawater with the Earth's crust, or they reduce sulfate to sulfide, harnessing chemical gradients to power their metabolism. A few may even use radioactive decay as an energy source, a process once thought too inefficient to sustain life. Each of these strategies is a reminder that life's ingenuity knows few limits, and that even in the most hostile environments, it finds a foothold. One of the most mysterious inhabitants of the deep is the xenophyophore, a type of giant single-celled organism that builds elaborate structures from sediment particles. These structures can be several centimetres across and often resemble sponges or coral, though they are composed of a single living cell. Xenophyophores are remarkably abundant in deep-sea trenches, covering large areas of the sea floor. They act as ecosystem engineers, creating habitats for other organisms and influencing the flow of nutrients through the sediment. Despite their importance, they remain poorly understood. How they grow to such enormous sizes, how they reproduce, and how they interact with other organisms are questions that scientists are only beginning to answer. Other creatures are known not from direct observation, but from the traces they leave behind. Trails in the sediment suggest the presence of burrowing worms and other infaunal animals. Tiny fecal pellets mark the feeding activities of amphipods and holothurians. Biochemical signatures in the water hint at the presence of organisms too small or too fragile to capture. The deep ocean is vast and difficult to study, and much of its life remains hidden from our eyes. What we do know is likely only a fraction of what exists. Every expedition to Challenger Deep reveals new species, new forms, new ways of surviving in the dark. The trench is not a static environment but a frontier, constantly surprising us with its diversity. Bioluminescence is one of the most striking adaptations in this realm. In a world without sunlight, light becomes a precious commodity, and many organisms have evolved the ability to produce it themselves. Some use bioluminescence as camouflage, matching the faint light from above to make themselves invisible to predators below. Others use it to attract prey, luring them closer with glowing lures or flashing patterns. Some use it to communicate, signaling potential mates or warning rivals. Even microbes can produce light, creating faint glows that drift through the water. Bioluminescence is not rare in the deep. It is common, woven into the fabric of life in the black. The mechanisms behind this light are chemical. Organisms produce light by oxidizing a molecule called luciferin, catalyzed by an enzyme called luciferase. The reaction produces photons with minimal heat, a phenomenon known as cold light. The colour of the light depends on the chemical structure of a luciferin and the conditions of the reaction. But most deep-sea bioluminescence is blue or green, the wavelengths that travel farthest through water. Some animals can even control the timing and intensity of their light, turning it on and off in pulses or waves. In the darkness of the trench, these displays can be startlingly beautiful. Brief, silent flares that pierce the blackness like stars in a night sky. The creatures of Challenger Deep are not just remarkable for their adaptations, they are remarkable for their rarity. Life here is sparse, scattered, and often solitary. The vast majority of the trench is empty water and sediment, with organisms few and far between. This scarcity shapes their behaviour and their interactions. Many deep-sea animals are opportunistic feeders, taking advantage of any food they encounter. Some are scavengers, consuming whatever falls from above. Others are predators, lying in wait for the rare prey that passes by. Competition is fierce but infrequent, and cooperation, when it occurs, is often subtle and indirect. The rhythms of life here are slow. Growth rates are low, reproduction infrequent. Many deep-sea species live for decades or even centuries, their life histories stretched out over timescales that make our own seem brief. Energy is too precious to waste on rapid growth or frequent reproduction. Instead, life invests in longevity and resilience. Some amphipods may take years to reach maturity. Some microbes divide only once every few years. Even the decay of organic matter is slow, with some sediments preserving recognizable organic molecules for tens of thousands of years. Time itself moves differently here, drawn out by the scarcity of energy and the constancy of conditions. The creatures of the trench are not isolated from the surface world, but their connection to it is tenuous and delayed. Food that falls from above may take months or years to reach the bottom, drifting slowly through the water column. Once there, it is quickly consumed by scavengers and decomposers. Large food falls, like a whale carcass, are rare events but can support entire communities for decades. As the carcass decomposes, it goes through stages, first attracting large scavengers, then smaller invertebrates, and finally bacteria that break down the remaining lipids and bones. Each stage supports a different set of organisms, and together they form a microcosm of the deep-sea ecosystem. These events remind us that life in the trench is not isolated. It is connected, however distantly, to the world above. Even in such a remote and extreme environment, traces of human activity are present. Microplastics have been found in the guts of amphipods collected from Challenger Deep. Chemical pollutants, including industrial compounds and radioactive isotopes, have been detected in the sediments. These contaminants arrive from the surface, carried by ocean currents and atmospheric circulation. Their presence is a stark reminder that no part of Earth is untouched by human influence. Yet life endures even this intrusion, adapting once again to conditions it did not create. Studying these ghostly inhabitants is not easy. The pressures of the deep make it difficult to collect live specimens, and many organisms are too fragile to survive the journey to the surface. Remote-operated vehicles and autonomous landers have provided glimpses into their world, capturing images and videos that reveal their forms and behaviours. Still, much remains unknown. How do these organisms reproduce? How do they find mates in such a vast and empty space? What roles do they play in the ecosystem? Each question leads to another, and each answer deepens the mystery. What is clear is that the trench is not a barren void. It is a living world, shaped by the same forces that shape life everywhere: energy, matter, evolution, and time. The creatures that inhabit it are not relics or anomalies. They are the latest expressions of life's relentless adaptability, the outcome of billions of years of experimentation. They show us that life is not limited by the conditions we find comfortable. It can thrive in darkness, under crushing pressure, in near-freezing temperatures, with little food and no light. It can become something unrecognizable to us and still flourish. The ghosts in the black are also windows into the past. Many deep-sea organisms retain features that have changed little over millions of years, preserved by the stability of their environment. Studying them can reveal insights into the early evolution of life on Earth and the conditions under which it first arose. Some scientists believe that life may have originated in environments similar to those found in the deep ocean, dark, high pressure, and fueled by chemical energy. If that is true, then the organisms of Challenger Deep are not just survivors of extreme conditions, they are echoes of life's beginnings, living reminders of where we came from, and perhaps they are also hints of what life might become elsewhere. If life can exist here, it can exist in the subsurface oceans of Europa, in the methane seas of Titan, or in the deep aquifers of Mars. The strategies used by amphipods and xenophyophores, by snailfish and microbes, are not tied to Earth. They are universal solutions to universal challenges: how to maintain structure under pressure, how to harvest energy in the dark, how to reproduce when encounters are rare. These solutions could emerge wherever conditions allow, whether beneath 11 kilometers of Pacific water or beneath a crust of alien ice. The deep teaches us that life is not fragile. It is stubborn, ingenious, and persistent. It adapts to its environment, bending physics and chemistry to its will. It builds bodies out of softness instead of strength, membranes that flex instead of fracture, proteins that fold differently under pressure. It uses light not from the sun but from its own chemistry. It feeds on the slow rain of death from above or on the invisible gradients of energy in the rocks below. It is everywhere it can be, and perhaps in places we have not yet imagined. These ghosts are not phantoms in the sense of being insubstantial or unreal. They are ghosts because they live beyond the reach of our senses, because they move through a world we cannot easily enter, because their existence is a reminder of how much remains unseen. They are proof that the absence of light is not the absence of life, and that the deep ocean is not a void but a vast complex living system. And as we continue our descent into Challenger Deep, they are the companions that guide us, silent, alien, and endlessly fascinating, moving through the black as though it were the most natural thing in the world. Beneath the weight of the ocean and within the stillness of the trench, there exists a realm so small that even our most advanced machines often overlook it. It does not flicker with bioluminescent light or swim gracefully through the black water. It does not leave tracks in the sediment or ripple currents with its passing. And yet, this hidden world is everywhere, woven into the mud, suspended in the water, clinging to rocks, and even living inside the bodies of larger creatures. It is the invisible kingdom, a vast, intricate, and astonishingly active network of microbial life that forms the true foundation of Challenger Deep. Without it, the trench would not function. Without it, the ghosts in the black would not exist. This kingdom is the quiet engine that keeps everything alive. It is easy to underestimate microbes because they are invisible to the naked eye, but in terms of numbers, diversity and influence, they dominate the deep. A single gram of trench sediment can contain billions of microbial cells, representing thousands of species. They live in layers just millimeters thick, yet those layers stretch for kilometers across the sea floor. They persist in conditions that would kill almost anything else. Crushing pressure, near freezing temperatures, total darkness, and severe nutrient scarcity. And they do more than just survive. They shape the chemical and biological landscape of the trench in ways that ripple upward through the entire ecosystem. The most fundamental role these microbes play is in breaking down organic matter. As marine snow drifts down from the surface and settles on the seafloor, it becomes food for microbial communities. These microbes decompose complex molecules into simpler ones, releasing nutrients that other organisms can use. In doing so, they recycle carbon, nitrogen, phosphorus, and other essential elements, keeping them available for life in the trench. Without this constant microbial activity, organic material would accumulate and become locked away, and the food web would collapse. Even the amphipods and snailfish that dominate the visible world of Challenger Deep rely on the invisible kingdom to sustain the flow of energy that ultimately feeds them. But microbes do much more than recycle waste. Many are chemolithoautotrophs, organisms that derive energy not from sunlight or organic matter, but from inorganic chemical reactions. In the sediments of Challenger Deep, chemical gradients form where seawater interacts with the minerals of the Earth's crust. These gradients provide energy that microbes can exploit. Some oxidize ammonia into nitrate, others convert hydrogen sulfide into sulfate, and still others use hydrogen or methane as energy sources. These reactions are the deep-sea equivalent of photosynthesis, primary production that does not depend on sunlight. It is a form of life that turns stone and water into sustenance, transforming geology into biology. This process is especially important in a place like Challenger Deep, where sunlight and photosynthesis have no reach. Chemolithoautotrophic microbes form the base of a food web that is independent of the surface. They produce organic molecules that feed other microbes, which in turn become food for small invertebrates, which then feed larger animals like amphipods and snailfish. In this way, the invisible kingdom builds ecosystems from the bottom up, powering life in a realm where traditional energy sources are absent. It is a subtle and slow process, but it is the backbone of the trench's productivity. Microbes also play a crucial role in regulating the chemistry of the deep ocean. They participate in the nitrogen cycle, converting nitrogen between different chemical forms and making it available to other organisms. They drive the carbon cycle, breaking down organic matter and storing carbon in sediments. Some even fix carbon directly from dissolved carbon dioxide, turning an inorganic gas into the building blocks of life. Through these processes, microbes influence not just the trench, but the entire ocean. The deep sea stores vast amounts of carbon, and microbial activity determines how much of it is locked away and how much returns to the water and atmosphere. In this way, the invisible kingdom affects Earth's climate, linking the dark depths of Challenger Deep to the air we breathe. Some microbes go beyond these familiar processes, exploiting energy sources that seem almost impossible. A few species harness energy from radioactive decay, using electrons released by decaying isotopes to drive their metabolism. Others use the natural electric potentials that develop at the interface between seawater and rock. Some form symbiotic relationships with minerals, precipitating or dissolving them as part of their metabolic cycles. These capabilities expand our understanding of what life can do. They show that metabolism is not limited to a handful of chemical reactions, but is a flexible toolkit that life can adapt to almost any environment. Microbes also shape the physical structure of the trench. By binding sediment particles together, they influence how the seafloor behaves. Their metabolic byproducts can alter the chemistry of the water, changing the availability of nutrients and minerals. Some precipitate minerals directly, forming layers of carbonate or iron oxide. Others dissolve minerals, releasing elements into the environment. Over geological timescales, these processes can reshape the trench itself, altering its sediments and influencing how it interacts with the ocean above. The invisible kingdom is not just a passive occupant of the trench, it is an active participant in its formation and evolution. What makes this microbial world even more remarkable is its diversity. Genetic studies of trench sediments have revealed thousands of species, many of which are unlike anything found elsewhere on Earth. Some belong to entirely new branches of the tree of life. Others are related to microbes from hydrothermal vents, subglacial lakes, or deep subsurface rocks, suggesting that similar forms of life have adapted to a wide range of extreme environments. This diversity reflects the trench's stability and isolation. With little disturbance from the surface, microbial communities have had millions of years to diversify and specialize, exploring every possible metabolic niche. Some microbes in Challenger Deep are extremophils, thriving not just despite the pressure, but because of it. High pressure affects molecular interactions, enzyme function, and cell structure, but these organisms have evolved to depend on it. Their proteins may be unstable at surface pressure, their membranes too fluid, their enzymes too slow. They are, in a sense, native to the deep, unable to survive outside it. This specialization shows just how deeply the invisible kingdom is intertwined with its environment. It is not merely adapted to the trench, it is inseparable from it. The invisible kingdom does not exist in isolation. It interacts constantly with the visible world. Microbes colonize the surfaces of amphipods and snailfish, living in symbiosis with their hosts. Some provide nutrients in exchange for shelter. Others break down waste products or help their hosts digest food. These partnerships are vital to both partners. In a nutrient-poor environment, even a slight metabolic boost can mean the difference between survival and starvation. Symbiosis extends beyond animals too. Xenophyophores, those giant single-celled organisms that build elaborate structures from sediment, host complex microbial communities on and within their shells. These microbes in turn influence how xenophyophores grow and interact with their environment. Microbes also form the basis of complex food webs. Many larger organisms feed directly on microbial mats or consume detritus rich in microbial biomass. Even those that feed on other animals are indirectly dependent on microbial production, because their prey ultimately derives its energy from microbial processes. In this way, the invisible kingdom links all levels of the trench ecosystem, from the smallest bacteria to the largest fish. It is the foundation upon which everything else rests. Studying this hidden world is challenging. Most microbes cannot be cultured in the laboratory, and many cannot survive the journey to the surface. Pressure changes can kill them or alter their metabolism, and removing them from their natural environment often strips away the chemical gradients they rely on. To study them, scientists use high-pressure vessels that replicate trench conditions or analyze their genetic material directly from sediment samples. These techniques have revolutionized our understanding of deep-sea microbiology, revealing a world far more diverse and dynamic than anyone suspected. One of the most surprising discoveries is that microbial life extends far below the seafloor itself. Drilling into trench sediments has revealed active microbial communities hundreds of meters beneath the surface. These microbes live in pores within the rock, subsisting on chemical reactions that occur deep within the Earth's crust. Some of them may be tens of millions of years old, descendants of lineages that have persisted in isolation since long before humans existed. They blur the line between the biosphere and the geosphere, showing that life is not confined to the planet's surface but extends deep into its interior. The presence of these deep biospheres raises profound questions about the origin and persistence of life. Did life on Earth begin in environments like these, shielded from the harsh conditions of the surface and powered by chemical energy from the planet itself? If so, the invisible kingdom of Challenger Deep may offer clues to our own beginnings. Its microbes may resemble the earliest forms of life, ancient and simple but astonishingly adaptable. And if life can persist in the depths of Earth's crust, perhaps it can persist beneath the icy shells of distant moons or within the rocky interiors of other planets. The invisible kingdom is not just ancient, it is resilient. It endures not just pressure and darkness, but also disturbances from above. Pollutants that reach Challenger Deep can alter microbial communities, selecting for species that can degrade or tolerate new compounds. Some microbes have evolved the ability to break down plastic, metabolize hydrocarbons, or neutralize heavy metals. These abilities may have evolved in response to natural challenges, but are now applied to human ones. They demonstrate once again that life adapts, that even in the face of rapid change, the invisible kingdom finds new ways to persist. It also reminds us that life is not always where we expect it. For decades, scientists assumed that the deep ocean was nearly sterile, a biological desert too extreme for anything but the hardiest microbes. What they found instead was a thriving ecosystem, invisible but essential, more complex than anyone had imagined. Every sample taken from the trench reveals new genetic lineages, new metabolic pathways, new adaptations. Each discovery expands our understanding of what life is and where it can exist, and with every new insight the boundaries of the possible shift a little further outward. This hidden world has practical implications as well. Enzymes from deep-sea microbes are being studied for use in biotechnology, where their stability under pressure and low temperature makes them valuable for industrial processes. Microbial metabolic pathways could inspire new methods of carbon capture or pollution cleanup. Understanding how microbes store and release carbon in the deep ocean could improve climate models and help predict how the planet will respond to human activity. The invisible kingdom is not just a curiosity. It is a source of knowledge and potential that we are only beginning to explore. Despite its importance, this microbial world remains one of the least understood parts of the biosphere. Most of its species have never been cultured, and many are known only from fragments of DNA. Their interactions, life cycles, and ecological roles are still largely mysterious. But one thing is clear: they are indispensable. Without them, the trench would not function. Organic matter would accumulate without being broken down. Nutrients would become locked away, unavailable to other organisms. The delicate balance of chemistry that sustains life would collapse. The invisible kingdom is not a background feature of Challenger Deep. It is its beating heart. The more we learn about this hidden realm, the more it reshapes our understanding of life as a whole. It shows that life is not dependent on sunlight or warmth or abundance. It shows that life is not limited to the planet's surface or even its oceans. It shows that life is not fragile but adaptable, not rare but abundant in forms we cannot see. It shows that the essence of life is not in the organisms we notice, the fish, the worms, the crustaceans, but in the microbes that sustain them. They are the quiet architects of ecosystems, the unseen engineers of the biosphere, the original and enduring inhabitants of our planet. The invisible kingdom also challenges how we think about ecosystems. We often imagine them as built from the top down, with large animals shaping the environment and smaller ones fitting in around them. In Challenger Deep, the reverse is true. The ecosystem is built from the bottom up, starting with the smallest organisms. Microbes shape the chemistry of the environment, which in turn shapes the biology. Their activity determines what nutrients are available, which influences which plants or animals, if any, can survive. Their metabolism creates the energy that fuels food webs. Their interactions form the foundation upon which everything else is built. It is a humbling reminder that the most important players in life's drama are often the ones we cannot see. And as we think about life elsewhere in the universe, the lesson of the invisible kingdom may be the most important of all. If life exists beyond Earth, it is unlikely to look like us. It may not have bones or muscles or even multicellular bodies, It may not build tools or civilizations. It may exist as simple, single-celled organisms, thriving in darkness and pressure, feeding on chemical gradients, invisible to the naked eye but no less alive. The microbes of Challenger Deep show us that such life is not only possible, it is likely. They show us that the building blocks of ecosystems are small, persistent, and astonishingly creative. They show us that the invisible can be more important than the visible, that the foundation can be more significant than the structure. The trench is often described as alien, but the truth is that it is profoundly Earth-like. It is part of our planet's deep interior, part of the vast and continuous system that connects atmosphere, ocean, crust, and life. The microbes that thrive there are not intruders from another world. They are Earth's oldest residents, still doing what they have done for billions of years, transforming energy, cycling nutrients, and sustaining ecosystems. They are not just inhabitants of Challenger Deep. They are the custodians of its balance, the builders of its complexity, and the keepers of its ancient rhythms. And as we continue deeper into this story, we begin to see that the trench's mystery is not only in the ghostly fish or the strange drifting amphipods, it is also in the invisible kingdom beneath them, a kingdom that does not announce itself with movement or light, but that quietly shapes everything around it. It is a reminder that even in the deepest darkness, the smallest forms of life hold the greatest power, and that the story of Challenger Deep is not just a story of what we can see, it is also a story of what we cannot. Even in the deepest, darkest corners of the ocean, in a place as remote and ancient as Challenger Deep, nothing is truly isolated. The water that presses down here began as raindrops falling from clouds. The carbon trapped in the sediments once cycled through forests and plankton blooms. The organic matter that sustains life here was once sunlight, captured by photosynthetic cells floating at the surface. No matter how far down you go, the fingerprints of the world above are everywhere. Challenger Deep is not a sealed chamber, cut off from the rest of the planet. It is a destination in a vast network of connections, a place that remembers the surface in countless subtle ways. And those echoes of the surface reach deeper and more persistently than we once believed. One of the most important links between the surface and the deep is marine snow, the slow, steady rain of organic material that drifts down through the water column. It begins with life near the surface, phytoplankton that capture sunlight and carbon dioxide, zooplankton that graze on them, fish and other animals that feed on both. When these organisms die, or when they produce waste, fragments of organic matter begin their descent. At first, they may be consumed by other creatures on the way down, broken into smaller and smaller pieces, but some of it escapes this gauntlet, continuing its long fall through the twilight and midnight zones, sinking through kilometers of water until it reaches the abyssal plains or the trench floor. This rain is slow. Some particles drift at just a few meters per day, but it is relentless. It is the primary source of energy for life in the deep, a distant echo of sunlight transformed into sustenance. Marine snow is not just dead material, it is alive. As it falls, it becomes colonized by bacteria and other microorganisms that break it down and recycle its nutrients. These microbial communities change the composition of the particles, releasing some nutrients back into the water and transforming others into forms that deep-sea organisms can use. By the time a flake of marine snow reaches Challenger Deep, it has been reshaped many times over, carrying with it the history of the journey it has taken. Each piece is a link between worlds, a message from the sunlit realm above delivered to the blackness below. The quantity and quality of this organic rain are influenced by what happens at the surface. When phytoplankton blooms are abundant, more organic matter is produced and more reaches the deep. When surface waters are nutrient poor, less is available. Climate patterns like El Niño can alter ocean circulation, changing the distribution of nutrients and the timing of blooms. Human activities also play a role. Fertilizer runoff from agriculture can cause massive algal blooms, increasing the amount of organic matter that sinks. Overfishing can disrupt food webs, altering how energy moves through the system. Even atmospheric changes like rising carbon dioxide levels affect the productivity of surface waters. The trench is far from the surface, but it's not immune to its rhythms. The echoes of those changes eventually reach even the deepest points. Sometimes, what reaches the trench is not a steady rain, but a rare, massive event. When a large animal like a whale dies and its carcass sinks, it creates a whale fall, a sudden pulse of organic matter that can sustain deep-sea communities for decades. At first, scavengers like hagfish and amphipods strip the flesh, consuming the soft tissues within weeks. Then smaller invertebrates arrive to feed on the remaining scraps. As the carcass decomposes, chemical gradients form, supporting specialized bacteria that use sulfide produced by decay as an energy source. Eventually, the bones themselves become habitats, colonized by organisms that feed on the fats within them. A single whale can support hundreds of species and shape the local ecosystem long after its fall. These events are rare, but their impact is profound, another reminder of how deeply the surface and the deep are intertwined. The surface also influences the deep in ways that are less visible, but equally significant. Tiny particles of dust and minerals carried by winds from continents eventually settle into the ocean and sink. These particles can travel thousands of kilometers before reaching the trench, bringing with them trace elements like iron and manganese that are essential for life. Rivers carry sediments and nutrients from land into the sea, and these too make their way into the deep. Even volcanic eruptions and wildfires leave their mark, sending ash and soot into the atmosphere that eventually settles into the ocean and drifts down. The trench is a collector of these distant events, a repository of material from across the planet. But not everything that arrives from above is natural. In recent decades, scientists have discovered that even Challenger Deep bears the unmistakable imprint of human activity. Microplastics, tiny fragments of plastic less than 5 millimeters across, have been found in the guts of amphipods collected from the trench. These particles originate from a wide range of sources: degraded packaging, synthetic clothing fibers, tire dust, and more. They're carried by currents and atmospheric circulation, slowly sinking until they settle into the deep-sea sediments. Some become embedded in the tissues of animals. Others are buried in the mud, forming a new geological layer that will mark the Anthropocene for millennia to come. Chemical pollutants have also reached the trench. Persistent organic pollutants like PCBs, banned decades ago, have been detected in deep-sea organisms. Heavy metals from industrial activity are present in the sediments. Even radioactive isotopes from nuclear testing and accidents have been found at the bottom of the ocean. These substances do not degrade easily, and they are transported across vast distances by ocean currents and atmospheric circulation. Their presence in Challenger Deep is a sobering reminder that no place on Earth is beyond our reach, and that the consequences of our actions extend far deeper than we often imagine. The biological impact of these contaminants is still being studied, but early findings suggest that they can affect deep-sea life in subtle but significant ways. Microplastics may interfere with digestion in amphipods and other scavengers, reducing their ability to extract nutrients from food. Chemical pollutants can accumulate in tissues, potentially altering metabolism or reproduction. Even low levels of radiation can affect microbial communities, changing their composition and activity. These changes ripple through the food web, affecting not just individual organisms but entire ecosystems. The trench is resilient, but it is not invulnerable. Climate change too is leaving its mark on the deep ocean. As global temperatures rise, ocean circulation patterns shift, altering how heat and nutrients move through the water. Warmer waters hold less oxygen, and oxygen minimum zones are expanding, pushing low oxygen conditions into deeper layers. These changes can affect the availability of nutrients that fuel surface productivity, altering the amount of organic matter that reaches the trench. They can also change the chemical environment of the deep, influencing microbial activity and nutrient cycling. Even small changes at the surface can have cascading effects that reach all the way to Challenger Deep. The carbon cycle provides one of the clearest examples of this connection. The deep ocean is the planet's largest reservoir of carbon, storing far more than the atmosphere and surface waters combined. Much of this carbon arrives as organic matter sinking from above. Some of it is consumed and respired back into carbon dioxide. Some is buried in sediments, where it can remain for millions of years. Microbial activity determines how much carbon is locked away and how much returns to the water and atmosphere. As climate change alters surface productivity and ocean circulation, it affects this balance, influencing how much carbon the deep ocean stores. In this way, the trench is both a recipient of surface change and a participant in global climate regulation. The echoes of the surface are not always harmful. Some are vital. Nutrients carried from land into the sea fuel plankton growth, increasing the flow of organic matter into the deep. Dust from deserts provides iron, a key element for marine productivity. Even the rhythmic cycles of the sun and moon, which drive tides and seasonal changes, shape the timing and magnitude of the reign of the life that sustains the trench. These connections remind us that the deep ocean is not separate from the rest of the Earth system. It is an integral part of it, influenced by and influencing everything from weather patterns to atmospheric composition. These echoes also reveal something profound about the nature of Earth as a system. Everything is connected. A tree growing on a distant hillside can, through a chain of events, influence the chemistry of Challenger Deep. Its leaves fall, decompose, and release nutrients into the soil. Rain carries those nutrients into a river, which flows into the ocean. Phytoplankton use those nutrients to grow, forming the base of the marine food web. When they die, some of their carbon sinks into the deep, where microbes transform it and bury it in the sediment. That carbon may remain there for millions of years, part of the slow geological cycles that regulate Earth's climate. A single leaf on a single tree can become part of the story of the deepest place on Earth. This interconnectedness also means that the trench is a valuable archive of Earth's history. Layers of sediment on the trench floor record changes in surface conditions over millions of years. Variations in the types and amounts of organic material reflect changes in productivity. Shifts in mineral composition record volcanic eruptions, dust storms, and even human activity. Isotopic signatures trace past climate changes, revealing how carbon and oxygen have cycled through the planet over time. By studying these layers, scientists can reconstruct a history of Earth's surface, written in the language of the deep. Challenger Deep is not just a place of biological and geological extremes, it is a library of the planet's memory. The trench also serves as a reminder of our responsibility. The fact that pollutants and plastics have reached such a remote place shows how far our influence extends. It challenges the idea that any part of Earth is untouched, that wilderness still exists in an absolute sense. Even here, where no sunlight has ever reached, and where pressure would crush most life, our presence is felt. The invisible kingdom must adapt to new chemicals. Amphipods consume fragments of plastic. The sediment layers record our industrial age. We have become part of the trench's story, whether we intended to or not. This realization does not diminish the resilience of the deep. If anything, it highlights it. Despite the changes we have imposed, life continues. Microbes evolve new metabolic pathways to break down pollutants. Animals adjust their diets and behaviors. Ecosystems reorganize themselves around new inputs. Life has always been a master of adaptation, and it remains so even now. But resilience has its limits. The deep ocean responds slowly, and rapid changes at the surface can outpace its ability to adapt. Understanding these limits is crucial if we hope to protect the trench and the countless other ecosystems connected to it. The echoes of the surface are a story of connection, but they are also a story of consequence. What we do in one part of the Earth system affects every other part, often in ways we do not anticipate. A chemical released into the atmosphere may fall as rain into a river, enter the ocean, and eventually settle into the trench. A change in land use may alter nutrient runoff, changing the productivity of surface waters and the amount of carbon stored in the deep. Even our emissions of greenhouse gases, released into the air above our cities, eventually shape the chemistry of the abyss. There is no away on a planet as interconnected as ours. Everything goes somewhere, and sometimes that somewhere is the deepest place on Earth. Yet this interconnectedness also offers hope. Just as negative changes reach the trench, so too can positive ones. Reducing pollution at the surface reduces the load that eventually reaches the deep. Restoring wetlands and forests can improve nutrient balance and slow the flow of harmful substances into the sea. Cutting greenhouse gas emissions can stabilize climate patterns and preserve the conditions that sustain deep-sea ecosystems. Our actions ripple outward, and those ripples do not stop at the shoreline. They continue downward, kilometre after kilometre, until they reach even the deepest trench. Challenger Deep, then, is not just a remote feature of the ocean floor. It is part of a global system that connects land, sea, air, and life. It remembers what happens above it, not in a conscious way, but in the sediments it collects, the chemicals it accumulates, and the life it sustains. It bears witness to volcanic eruptions, glacial cycles, human industry, and climate change. It tells a story that is not separate from ours, but entwined with it. And as we peer into its darkness, we are really looking into a mirror, one that reflects the choices we make far above. Even as the trench receives these echoes from the surface, it sends echoes back. The carbon it stores influences atmospheric levels and climate. The nutrients it traps or releases affect productivity in surface waters. The water masses that pass through it contribute to global circulation patterns that regulate weather and temperature. What happens here matters everywhere else. The deep and the surface are not separate realms. They're parts of a single, continuous system, each shaping the other in ways both subtle and profound. This reciprocity underscores the importance of understanding and protecting the deep ocean. It is not a distant curiosity, but a vital part of Earth's life support system. Its ability to store carbon, recycle nutrients, and sustain biodiversity affects the health of the entire planet. Its sensitivity to changes at the surface makes it a powerful indicator of environmental shifts, and its resilience offers lessons in adaptation and persistence that are as relevant to us as they are to the amphipods and microbes that call it home. As we continue our descent into Challenger Deep, the presence of the surface world becomes impossible to ignore. It is there in the organic particles that feed the invisible kingdom. It is there in the pollutants buried in the sediment. It is there in the chemical gradients that microbes exploit and the food webs that depend on them. It is there in the sediments that record Earth's history layer by layer. The trench may seem isolated, but it is deeply connected. A place where the farthest reaches of the planet come together, where distant storms, ancient forests and human cities all leave their mark. And in those echoes, we find a humbling reminder. Nothing we do is confined to where we do it. Every action reverberates through the system, sometimes in ways we cannot see, sometimes in places we will never visit. The deepest place on Earth remembers us, whether we wish it to or not. And in that memory lies both a warning and an invitation. A warning of the reach of our influence, and an invitation to wield that influence with care. For most of human history, the idea of exploring the deepest parts of the ocean was as far-fetched as travelling to the moon. The sea beyond the horizon was already a mystery. What lay beneath it, in the lightless reaches of the abyss, was almost unimaginable. People spoke of monsters and bottomless pits, of vast, unknown worlds beneath the waves, but they had no way to see them. Even as ships grew sturdier and sailors ventured farther, the depths remained beyond reach, sealed behind a wall of pressure that no wood, iron or bone could survive. Challenger Deep, the deepest known point on Earth, existed in complete isolation from human eyes and hands, a world known only by name and guesswork. It was the quest to understand that hidden realm that pushed some of humanity's boldest leaps in engineering and imagination. The ocean's surface could be crossed with ships and sails, but reaching its deepest floor required something entirely new. It demanded that we build machines that could withstand pressures greater than those found in any natural environment on land, where water could crush steel like paper. It required sealing humans inside tiny capsules that could survive conditions they were never meant to endure. It required, above all, a willingness to go where no one had ever gone, to sink into the blackness not knowing what awaited below. The first serious attempt to measure the depth of the Mariana Trench came not from a machine but from a ship. In 1875, the British vessel HMS Challenger, from which Challenger Deep gets its name, embarked on a pioneering scientific expedition to explore the world's oceans. Using weighted ropes and simple instruments, the crew measured depths, collected samples, and documented marine life. Near the Mariana Islands, they recorded a depth of more than 8,000 meters, a staggering figure for the time. They could not know it then, but their measurements were the first step toward revealing a place that would fascinate explorers for generations. Technology advanced slowly over the next century, but curiosity about the trench never faded. In the early 20th century, scientists began using echo sounding, bouncing sound waves off the seafloor, to map the ocean depths more accurately. By the 1950s, they had identified a point within the Mariana Trench, deeper than any other known location. It became known as Challenger Deep. Even then, the idea of sending humans there seemed impossible. The pressure at that depth was over 1,000 times greater than at the surface, more than enough to crush a battleship. No existing submersible could survive it, but impossibility has never stopped human curiosity for long. The breakthrough came with the development of a new kind of vessel, the bathyscaphe. Unlike earlier submersibles, which were tethered to ships and limited in depth, bathyscaphes were freediving, self-contained craft designed to reach extreme depths. They combined a buoyant float filled with gasoline, lighter than water and incompressible, with a heavy steel sphere that housed the crew. The most famous of these was Trieste, built in Italy and later purchased by the US Navy. Its pressure sphere was just over 2 meters wide, with walls up to 13 centimeters thick. Inside, 2 men could sit shoulder to shoulder, surrounded by controls, instruments, and a single small viewport. It was cramped, uncomfortable, and unlike anything that had ever descended so far. On January 23, 1960, Trieste made history. Piloted by Swiss engineer Jacques Picard and US Navy Lieutenant Don Walsh, the bathyscaphe began its descent into Challenger Deep. It took nearly 5 hours to sink through 11 kilometers of water, during which the crew experienced total darkness, freezing temperatures, and the constant awareness that millions of tons of water pressed against their fragile sphere. At around 10,116 meters, they reached the seafloor, a depth that remains close to the most accurate measurements even today. Through their small window, they saw a landscape of soft, light-coloured sediment and, to their astonishment, signs of life, a flatfish-like creature and small shrimp-like animals. It was proof that even here, where pressure and darkness seemed absolute, life endured. The descent of Trieste was a triumph of engineering and human endurance, but it was also a beginning rather than an end. The technology of the time was primitive by today's standards, and the mission gathered limited data. The bathyscaphe had no cameras capable of functioning at that depth, and its instruments were basic. It was a daring exploration, but one that left more questions than answers. Decades would pass before another human returned to Challenger Deep. In the meantime, robotic explorers began to take our place. Advances in materials, electronics, and remote control allowed engineers to build unmanned vehicles capable of withstanding the crushing pressures of the trench. These vehicles, known as landers, were equipped with cameras, sensors, and sample collectors. Unlike crude submersibles, they could spend long periods on the seafloor, recording data and capturing images. They revealed a landscape more complex than Piccard and Walsh had imagined. Rippled sediments, scattered rocks, and diverse communities of amphipods and microbes. They showed us that Challenger Deep was not a barren void, but a functioning ecosystem, alive and dynamic. The era of robotic exploration reached a milestone in 2012, when filmmaker and explorer James Cameron descended solo to Challenger Deep in a submersible called Deep Sea Challenger. Sleek and vertical, unlike the spherical bathyscarfs of the past, it was designed to slice through the water efficiently. Its pressure sphere was just large enough for one person, and its systems were built to operate autonomously, minimizing the need for external support. Cameron spent several hours on the seafloor, filming and collecting samples. He observed a desolate but fascinating landscape, with fine sediments and occasional rocks, and recorded footage of small creatures moving through the water. His descent was both a technological achievement and a testament to human curiosity, a reminder that even in the 21st century there are still places on Earth where few have gone. Since Cameron's dive, new missions have continued to push the boundaries of exploration. In 2019, American explorer Victor Vescovo made multiple dives to Challenger Deep in a submersible called DSV Limiting Factor, part of the 5 Deeps expedition. Built from titanium and engineered to withstand repeated dives, it was the first submersible capable of visiting the trench regularly rather than as a one-time feat. Vescovo's expeditions revealed new details about the trench floor and collected biological and geological samples. They also highlighted the presence of human impact even here. Plastic debris was found at the bottom, a sobering reminder that no part of the ocean is beyond our reach. Each new voyage into Challenger Deep has expanded our understanding of the abyss, but they have also underscored how much we still don't know. The trench covers an area larger than many countries, and only a tiny fraction of it has been explored directly. Much of it remains unmapped in detail. The diversity of life there is still poorly understood, with most species known only from a handful of samples. Even basic questions about how water circulates within the trench, how sediments accumulate, how ecosystems change over time, remain unanswered. Every mission answers one question and raises 10 more. The difficulty of exploration is part of the reason for this ignorance. Building a vehicle that can survive the trench's pressure is challenging enough. Sending it back repeatedly without catastrophic failure is even harder. Communication is limited because radio waves cannot penetrate water, forcing submersibles to rely on acoustic signals that are slow and prone to distortion. Navigation is difficult because GPS signals don't reach the deep ocean. Even collecting samples is a challenge, as delicate organisms often do not survive the journey to the surface. Every piece of data we gather from Challenger Deep is hard-won, the result of decades of incremental progress and hard lessons. Yet those hard-won pieces are worth it, because they offer more than just scientific knowledge. They offer perspective. Each descent into the trench is a reminder of how little of our planet we truly know. We have mapped the surfaces of Mars and the Moon in greater detail than we have mapped the floor of the Pacific. We understand more about the composition of distant stars than we do about the ecosystems thriving 11 kilometers beneath our feet. Challenger Deep humbles us. It reminds us that exploration is not a completed chapter of human history, but an ongoing story, one that still has many pages left to write. Voyages into the abyss also change how we see ourselves. For the men and women who have descended into Challenger Deep, the experience is transformative. Don Walsh described the silence and darkness as overwhelming, a reminder of the ocean's vastness. James Cameron spoke of the seafloor as an alien landscape, more like another planet than anything on Earth. Victor Vescovo described the profound stillness, broken only by the sound of his submersible systems and the occasional movement of unseen life. Each of them returned with a renewed appreciation for the planet's complexity and fragility. It is one thing to know intellectually that Earth's deepest places exist. It's another to sit among them, surrounded by millions of tons of water, and feel how small and temporary we are. The technology that makes these voyages possible has applications beyond exploration. Materials and designs developed for deep-sea submersibles inform spacecraft engineering, where high pressure is replaced by vacuum, but the need for structural integrity is the same. Robotic systems built to operate autonomously in the deep ocean inform designs for planetary rovers. Even the instruments used to study trench ecosystems, capable of detecting tiny chemical gradients and subtle biological signals, have parallels in the search for life elsewhere. Challenger Deep, in this way, becomes not just a destination but a proving ground, a laboratory for the technologies that will carry us into the solar system and beyond. The challenges faced by explorers of the trench are strikingly similar to those faced by explorers of space. Both environments are hostile to human life. Both require sealed, pressurized vessels. Both demand careful management of energy and resources. Both involve communication delays and navigational difficulties, and both remind us of the vastness of the unknown. It is no coincidence that many who have explored the deep are also involved in space exploration. They see the trench not as an end, but as part of a continuum, a place where we learn how to explore worlds beyond our own. There is also a philosophical dimension to these voyages. To descend into Challenger Deep is to confront the limits of human knowledge and capability. It is to face an environment that is indifferent to our presence, that exists on timescales and scales beyond our comprehension. It is to realize that our species, for all its intelligence and technology, is still just beginning to scratch the surface of what is possible. And yet it is also to feel the thrill of discovery, the same thrill that must have driven the first humans to cross oceans, climb mountains, or look up at the stars. The abyss humbles us, but it also calls to us. It is a reminder that exploration is not just about knowledge. It is about curiosity, courage, and the desire to understand our place in the universe. The people who descend into Challenger Deep are not the only voyagers. Robotic probes, autonomous landers, and remote sensors have become our eyes and hands in the deep. They operate in conditions that would kill us in an instant, sending back data and images from a world we cannot enter. They are extensions of our curiosity, machines built to go where we cannot. And as they grow more sophisticated, they will reveal more of the trench's secrets. Some will map the seafloor in unprecedented detail. Others will monitor currents and chemical fluxes. Some may even drill into the sediments, reaching into the geological record of Earth's history. These machines are the next wave of exploration, and their journeys will take us deeper into the unknown than ever before. Each mission into Challenger Deep adds a new layer to our understanding, but it also deepens the mystery. The more we learn, the more complex the picture becomes. We discover new species, but we do not yet know how they live or interact. We map new geological features, but we do not fully understand how they formed. We measure chemical gradients, but we do not yet know how they change over time. The trench resists easy answers. It's a place where every discovery is a beginning, not a conclusion. And perhaps that is why these voyages matter so much. They remind us that exploration is not about conquering the unknown, but about engaging with it. It is not about planting a flag and declaring victory, but about asking questions and seeking answers. It is about humility. The humility to know that the world is larger, stranger, and more complex than we can imagine, and the willingness to learn from it. Challenger. Deep is not a prize to be claimed. It is a teacher, and every descent is a lesson. As we look to the future, those lessons will guide us. New materials and technologies will allow submersibles to dive deeper, stay longer, and explore more widely. Networks of autonomous sensors will map the trench in real time, revealing its currents, chemistry, and biology in unprecedented detail. Sample return missions may bring back intact organisms or cores from deep within the sediments, unlocking secrets of evolution and Earth's history. International collaborations will expand our capacity to explore, combining expertise and resources from around the world. The age of trench exploration is only just beginning, and its future promises discoveries that we can barely imagine today. And as we push deeper into Challenger Deep, we will not only learn about the trench itself, we will also learn about ourselves, about our ingenuity, our persistence, and our endless curiosity. We will see reflected in the abyss our own drive to understand, to explore, to reach beyond what is known, and in doing so, we will be reminded that even the deepest, darkest, most remote places on Earth are part of our shared world, places that shape the planet we live on and the future we build. The voyages into the abyss are few, but they carry with them all of humanity's questions and hopes. Their journeys are not just expeditions into a physical space, but into the unknown itself. They remind us that exploration is not finished, that there are still frontiers left on our own planet, and that understanding them is as important as reaching for the stars. Challenger Deep is not just a destination, it is a beginning, a place that teaches us what it means to explore and why exploration matters at all. Standing at the bottom of Challenger Deep, even in imagination, you cannot help but think of other worlds. The pressure is beyond comprehension, the darkness complete, the temperature barely above freezing. There is no sunlight here, no seasons, no weather, no sign of the familiar rhythms of surface life. And yet, despite all of that, this place is alive. It is home to fish and amphipods, to single-celled giants and microbial kingdoms, to ecosystems that function in ways so alien to us that they might as well belong to another planet. That fact, that life can flourish in a realm so far removed from the conditions we think of as normal, is not just fascinating, it is profoundly important. Because if life can exist here, it forces us to rethink where else it might exist, and what it might look like when we find it. For most of human history, we imagined life as something fragile, bound tightly to the conditions we know. We assumed it needed warmth and light, air and land, the gentle balance of seasons and cycles that sustain us. When we thought of other worlds, we looked for places that resembled Earth, planets with temperate climates, liquid water on the surface, and atmospheres like our own. It seemed obvious that life could only exist where Earth-like conditions existed. But the trench tells a different story. Here, life thrives in crushing pressure, in absolute darkness, without sunlight, and often with little organic matter. It draws energy from chemical reactions, not from the sun. It builds cells and tissues that depend on pressure to function. It exists in forms we never would have predicted. If life can do that here, why should we assume it cannot do the same elsewhere? Some of the most promising places to look for life beyond Earth are in many ways like Challenger Deep. Jupiter's moon Europa, for example, is covered by a thick shell of ice, beneath which lies a global ocean of liquid water. That ocean is cut off from sunlight, isolated from the surface by tens of kilometers of ice. Yet it may be heated from below by tidal forces and hydrothermal activity, creating chemical gradients that microbes could exploit. If life exists there, it would likely resemble the invisible kingdom of the trench. Single-celled organisms living off chemical energy, thriving in darkness, and forming the base of ecosystems that do not depend on light. It would not look like the forests or fish or birds of Earth's surface. It would look more like the microbial mats clinging to trench sediments, or the chemosynthetic communities around deep-sea vents. Saturn's moon, Enceladus, offers a similar story. Geysers of water vapour and ice particles erupt from its south pole, hinting at a subsurface ocean beneath its icy crust. Those plumes contain organic molecules and salts, evidence that chemical reactions are occurring below. The environment there may be cold and dark, but so is Challenger Deep, and life thrives here nonetheless. If organisms exist beneath Enceladus's ice, they may feed on chemical energy from interactions between water and rock, just as trench microbes do. They may form biofilms in the sediment or drift through the water column, invisible but vital. Studying the deep ocean is, in a sense, a rehearsal for studying worlds like Enceladus. It shows us how life might organise itself in places where sunlight never reaches. Even Mars, long thought to be a dry and barren planet, may harbour environments analogous to the trench. Beneath its surface, where pressure and temperature are stable and radiation is shielded, pockets of liquid water may persist. Chemical reactions between rock and water could provide energy for microbial life, just as they do in the deep ocean. If such life exists, it would almost certainly be microbial, and it would likely bear little resemblance to anything on Earth's surface. But it might look familiar to anyone who has studied the invisible kingdom, cells clinging to mineral grains, metabolizing hydrogen or sulfur, forming slow-growing colonies that persist for millions of years. The lessons Challenger Deep offers are not limited to specific worlds. They also change how we think about the very nature of habitability. Traditionally, we have defined the habitable zone as the region around a star where liquid water can exist on a planet's surface, but the trench reminds us that life does not need a surface at all. It does not need sunlight or an atmosphere. It needs water, yes, but it also needs energy, and that energy can come from chemistry, not just from starlight. It needs stability, but that stability can exist beneath kilometers of ice or rock. It needs nutrients, but those can be supplied by geological processes, not just by surface ecosystems. Challenger Deep shows us that habitability is not a narrow range of conditions, but a spectrum, and that life can find a foothold in places far outside the boundaries we once imagined. It also shows us that life can adapt in ways we would not predict. The snailfish that lives at 8,000 meters depends on pressure for its proteins to function. Amphipods build their exoskeletons without calcium carbonate, which dissolves at great depth. Microbes use chemical energy sources we once thought too weak to sustain life. These adaptations are not trivial. They represent fundamental changes to the way life works, and they suggest that if life exists elsewhere, it may be built on principles we do not yet understand. Its biochemistry may differ from ours. Its cells may use molecules unfamiliar to us. Its strategies for survival may seem alien not because they are impossible, but because we have not yet imagined them. Even the structure of ecosystems in Challenger Deep challenges our assumptions. On the surface, ecosystems are often built around abundant energy sources. Plants capture sunlight, herbivores eat plants, carnivores eat herbivores, and energy flows upward through the food web. In the deep ocean, the flow is different. Energy is scarce and arrives slowly, often from distant sources. Food webs are built on detritus, on marine snow, on chemical gradients. Organisms grow slowly and live long lives. Populations are sparse, and interactions are rare. These are not flaws, but adaptations to a world where energy is precious. If we find life on Europa or Enceladus, we should expect similar patterns. Ecosystems that function not through rapid growth and turnover, but through patience and efficiency. The trench also teaches us that life can persist for astonishing lengths of time in stable environments. Microbes deep within the sediments may be descendants of lineages that have existed for tens of millions of years. They reproduce slowly, sometimes dividing only once in a century, yet they endure. They are not thriving in the way we usually think of life thriving, but they are alive, metabolizing, evolving. If life exists elsewhere, it may follow a similar path, existing in a low-energy state, persisting quietly for eons, changing so slowly that we might overlook it. Such life might not announce itself with obvious signs. It might not reshape its environment in ways we can easily detect, but it would still be there, holding on in the dark. Challenger Deep also reminds us that life can be resilient to change. The microbes there have adapted to pollutants that have made their way into the trench. Amphipods ingest microplastics and continue to survive. Chemical shifts caused by climate change ripple downward, and still, the invisible kingdom persists. This resilience suggests that life elsewhere might also be able to adapt to conditions we would consider extreme or unstable. It might tolerate high radiation levels, fluctuating temperatures, or unusual chemistries. It might find ways to use materials we see as toxic. Life is not static. It is a problem solver, constantly finding ways to exist in whatever conditions it encounters. Even the physical realities of the trench, the pressure, the darkness, the cold, mirror environments we expect to find beyond Earth. The pressure beneath Europa's ice may rival or exceed that of Challenger Deep. The darkness of Enceladus's ocean is as absolute as the darkness here. The cold of a Martian aquifer is not far from the near-freezing temperatures of the trench. If life can adapt to these conditions here, it can adapt to them elsewhere. The trench is, in this sense, a natural laboratory for astrobiology, a place where we can study how life behaves under conditions similar to those that might exist on other worlds. Our exploration of Challenger Deep also offers practical lessons for how we might search for life beyond Earth. The tools we develop to explore the deep ocean, pressure-resistant submersibles, autonomous landers, instruments capable of detecting subtle chemical signatures, are prototypes for the probes we might one day send to Europa's ocean or Enceladus's plumes. The techniques we use to study microbial communities in the sediments, extracting DNA, analysing isotopic ratios, identifying metabolic pathways, are the same techniques we will use to study samples from other planets. Even the challenges we face in exploring the trench, communication delays, navigation without GPS, the difficulty of retrieving fragile samples, mirror the challenges of planetary exploration. By learning how to overcome them here, we prepare ourselves to overcome them elsewhere. The trench also shapes how we interpret potential signs of life when we find them. For example, the detection of organic molecules on another world does not necessarily mean that life is present. Organic molecules can form through abiotic processes as well. But in Challenger Deep, we see how certain patterns, specific ratios of isotopes, particular combinations of molecules, distinct spatial distributions, are associated with biological activity. These biosignatures can help us distinguish between life and non-life elsewhere. Similarly, the discovery of chemical disequilibria, conditions where chemical reactions are out of balance, may hint at biological processes just as they do in the deep ocean. The diversity of life in Challenger Deep also cautions us against narrow expectations. We might be tempted to look for life that resembles what we know: photosynthetic cells, multicellular organisms, complex ecosystems. But the trench shows us that life can take forms that are invisible to us, that do not fit our preconceived categories. It can be microbial, slow-growing, metabolically simple. It can exist without oxygen, without sunlight, without many of the features we associate with habitability. If we focus too narrowly on Earth-like life, we may miss what is actually there. The trench teaches us to broaden our search, to look for signs of life we might not immediately recognize. It also teaches us humility. Despite decades of exploration, we still know only a fraction of what lives in Challenger Deep. Each new expedition reveals new species, new metabolic pathways, new forms of adaptation. If we know so little about life on our own planet, how much less must we know about life elsewhere? The trench reminds us that discovery is a process, not a moment. It takes time, patience, and persistence. It requires us to ask questions we do not yet know how to answer, and it demands that we remain open to surprises, because life, as Challenger Deep shows us, is full of them. There is another, subtler lesson here too. Life in the trench is not separate from its environment. It is shaped by the pressure, the darkness, the scarcity. It depends on the geological processes that create chemical gradients, on the slow rain of organic matter from above, on the circulation of water through the ocean. It is not an invader imposed on the environment, but a part of it, inseparable from the conditions that sustain it. If life exists elsewhere, it will likely be the same. deeply entwined with its environment, shaped by and shaping it in turn. Understanding that relationship is key to recognizing life when we see it. Even the way we think about planetary protection is influenced by what we learn here. Just as delicate trench ecosystems can be altered by the introduction of foreign substances, so too could extraterrestrial ecosystems be affected by our presence. The more we understand how life interacts with its environment in extreme places like Challenger Deep, the better prepared we are to explore other worlds responsibly, to search for life without destroying it, to learn without contaminating. In many ways, Challenger Deep is a reminder that the universe is not as inhospitable as it seems. When we look into space, we see vast stretches of vacuum, icy moons, scorched planets, and frozen comets, places that, at first glance, appear utterly lifeless. But if life can persist beneath the 11 kilometers of water, under crushing pressure and in complete darkness, then perhaps it can also persist beneath an icy crust, or in a subsurface aquifer, or deep within a planet's rocks. Perhaps life is not rare but common, not fragile but resilient, not confined to narrow bands of conditions but capable of thriving in many. The trench also offers a more philosophical lesson. It shows us that life's essence is not tied to any specific environment. It is not defined by warmth or light or abundance. It is defined by its ability to adapt, to find a way, to exist against the odds. Life is not a thing that happens only under ideal conditions. It is a force that shapes itself to whatever conditions it encounters. And if that is true here, it may be true everywhere. The universe may be filled with life, not because it is like Earth, but because life, wherever it arises, is capable of becoming like whatever place it finds itself in. As we continue to explore Challenger Deep, we are not just exploring a place on Earth. We are exploring an analogue for worlds beyond our planet. We are learning how life behaves when light and air and warmth are stripped away. We are learning how ecosystems organize themselves in environments far from the conditions we evolved in. And in doing so, we are preparing ourselves for the day we look into the oceans of Europa or the subsurface of Mars and ask the same questions we ask here. What lives here? How does it survive? What does it tell us about life itself? These questions are not just scientific. They are deeply human. They speak to our desire to know whether we are alone, to understand our place in the cosmos, to see whether the story of life is a story unique to Earth or a chapter in a much larger book. Challenger Deep suggests that the latter is more likely. It tells us that life is more versatile, more adaptable, more inventive than we once thought. It tells us that the conditions we see as extreme may not be extreme to life at all. And it tells us that if life can flourish here, in the deepest, darkest part of our own world, then perhaps it flourishes elsewhere too, waiting for us to find it. The abyss beneath the Pacific is, in many ways, a bridge, a connection between our familiar world and the alien worlds we hope to explore. It shows us that the line between the two is thinner than we think. The deep ocean is as alien to us as Europa's ocean would be. The microbes in its sediments are as strange as anything we might find on Mars. The adaptations of its inhabitants are as radical as those we imagine for life on distant moons. By studying Challenger Deep, we do not just learn about Earth. We learn about the universe. And in doing so, we come a little closer to answering one of humanity's oldest and most profound questions. Are we alone? Perhaps in the end, that is Challenger Deep's greatest gift. It does not just reveal the resilience of life on Earth. It expands our imagination for what life can be. It challenges our assumptions, broadens our definitions, and invites us to look beyond the narrow boundaries we once drew. It tells us that life is not a rare accident that happens only under perfect conditions. It is a fundamental property of the universe, capable of arising and enduring in the most unlikely places. And if that is true, then the darkness beneath the Pacific and the darkness beneath Europa's ice are not so different. Both may be alive. Both may hold stories we have yet to hear. Both may remind us that life, wherever it is always reaching outward, always finding a way, always expanding the possible. There's a moment, if you think about Challenger Deep long enough, when the story stops being about a place at the bottom of the ocean and starts being about something far more intimate. It begins as a curiosity, a trench deeper than Mount Everest is tall, hidden beneath kilometres of water, home to strange creatures and ancient microbes. But the longer you sit with it, the more it feels like a mirror. It reflects something about the world we live in, but also about us, about how we think, how we grow, how we survive. The abyss, for all its alien darkness, is not just a physical space at the edge of the map. It is also an idea. It is a metaphor for the hidden depths within us, the parts of ourselves shaped by pressure, silence, and time. And if we listen carefully to what Challenger Deep is telling us, we might learn something about more than just the ocean. It's easy to think of the abyss as a place apart, separate from the rest of the world, cut off by distance and darkness, but it is not. It is connected to the surface by the slow rain of marine snow, by the movement of water masses, by the gravity that draws particles downward. It is influenced by storms, seasons, and climate cycles. It remembers volcanic eruptions, human pollution, and even the rise and fall of civilizations in the sediments it collects. It is a part of the same planet we inhabit, governed by the same physical laws, shaped by the same geological and biological processes. The abyss is not an exception, it is an extension, and perhaps the same is true of the hidden parts of ourselves, the ones we do not often see or speak of. They are not separate from who we are, they are part of us, shaped by our experiences, connected to everything else we do. There is something profoundly human about the way life endures in Challenger Deep. It is shaped by pressures beyond anything we can imagine, yet it persists. It is cut off from the light, yet it finds ways to grow. It exists in scarcity and isolation, yet it builds ecosystems and sustains complexity. It is not loud or dramatic. It is quiet, deliberate, and patient. And isn't that, in some ways, how we survive too? Under pressure, we adapt. In darkness, we learn to sense in new ways. In scarcity, we find value in small things. Life in the trench does not rage against its environment, it bends with it. It does not demand that the world change to suit it. It changes to suit the world. There is a lesson in that. A lesson about resilience, about flexibility, about the strength that comes not from resisting change, but from absorbing it and becoming something new. We tend to think of pressure as a force that crushes, that breaks things down, and in many cases it does. But in Challenger Deep, pressure is not just a challenge, it is a condition of life. Many organisms there cannot survive without it. Their proteins fold differently, their membranes function differently, their entire biochemistry depends on it. They are not just enduring pressure, they are defined by it. It is part of who they are, and maybe the same is true for us. The pressures we face, the struggles, the stresses, the responsibilities, are not just obstacles to be overcome. They shape us. They build strength, patience, and perspective. They teach us what we are capable of. Like the snailfish that cannot live above a certain depth, we are shaped by the conditions we endure. They leave their imprint on us, not as scars but as structure. The darkness of the trench is another condition we might think of as hostile, yet life there has turned it into something ordinary. It does not lament the absence of light. It uses other senses. It produces its own glow. It communicates and hunts and navigates without the need for sight. The darkness is not an absence but a medium, a space in which life can exist in forms we never imagined. We often speak of the darkness within us, the fears, the doubts, the parts of ourselves we prefer not to confront, as something negative, something to be eradicated. But maybe, like the darkness of Challenger Deep, those parts of us are not empty. Maybe they are spaces where new ways of being can emerge, Maybe they are conditions under which hidden strengths come to life. Even scarcity, which on the surface seems like a limitation, becomes a source of creativity in the trench. Energy is scarce there, so organisms evolve to use it efficiently. Growth is slow, but it is steady. Populations are small, but they are stable. Life does not squander resources, it builds systems that endure. We live in a world that often celebrates abundance. More food, more money, more information. But the trench reminds us that scarcity has its own wisdom. It forces choices, it demands efficiency, it teaches patience, and it shows that thriving is not always about having more. Sometimes it is about doing more with less. The invisible kingdom of microbes in the trench offers another lesson. It reminds us that the most important things are often the ones we cannot see. These microbes drive nutrient cycles, shape ecosystems, and sustain life, yet they are invisible to the naked eye. Without them, nothing else could exist. In our own lives, the invisible forces, our thoughts, habits, relationships, beliefs, shape everything we do. They operate quietly, often unnoticed, but they are the foundation of who we are. Paying attention to them, nurturing them, understanding how they work can transform how we live. Just as the trench cannot exist without its microbial engine, we cannot flourish without tending to the unseen parts of ourselves. The deep also teaches us about time. Life there moves slowly. Microbes may divide once in a century. Amphipods grow over years. Sediments accumulate millimetre by millimetre over millennia. Nothing happens quickly, but everything happens. The trench is a realm of patience, where change unfolds over timescales far longer than a human life. We live in a world that prizes speed, fast results, quick decisions, immediate gratification. But the abyss reminds us that some of the most profound changes take time. Growth is often slow, healing is often gradual. Understanding unfolds layer by layer, like sediment on the seafloor. And that's not a flaw. It's part of how complexity arises. It's part of how strength is built. There's humility in the trench too, a kind of quiet acceptance of what is. Life there does not try to remake the environment into something else. It does not seek to eliminate the darkness or reduce the pressure. It works with what exists. It finds niches, exploits gradients, uses what is available. It adapts rather than resists. That doesn't mean it's passive. It is active, creative, relentless. But its creativity is grounded in reality. It works with the conditions it has, not the ones it wishes for. There's wisdom in that, for us as well. We spend much of our lives trying to change what cannot be changed. The past, other people, the nature of the world. But sometimes the path forward is not to resist, but to adapt. Not to fight the pressure, but to let it shape us into something stronger. The trench is also a place of connection. It is linked to the surface by the slow rain of marine snow, to the deep earth by chemical gradients, to the rest of the ocean by currents. It is not isolated, even if it seems so, and neither are we. The parts of ourselves that feel cut off, the parts we hide, the parts we do not speak about, are still connected to everything else we are. They influence our choices, shape our actions, and connect to others in ways we may not realize. A small change deep within us can ripple outward, just as a shift in surface productivity can alter the flow of energy to the trench. Understanding those connections, acknowledging that the surface and the depths are part of the same whole, is part of understanding ourselves. Exploring Challenger Deep has also taught us something about the nature of curiosity. It shows us that curiosity is not just about seeking the spectacular. It is about being willing to go where it is difficult, to spend years building machines to descend into a place that most people will never see. It is about asking questions without knowing if answers exist. It is about persistence in the face of uncertainty. And perhaps that is a reflection of how we explore ourselves. Understanding who we are is not a straightforward journey. It requires patience, effort, and the willingness to look into the darker, deeper parts of ourselves, the ones that resist easy explanation. The trench teaches us that what is most worth knowing is often what lies deepest and is hardest to reach. Even the act of exploring the trench itself mirrors our internal journeys. The descent is slow and deliberate. Each layer of the ocean brings new challenges, changes in temperature, pressure, and light. Each requires adaptation and resilience. Reaching the bottom is not a conquest, but a process, and so it is with self-discovery. We descend layer by layer, encountering new aspects of ourselves, adapting to new insights, learning to see in the dark. The goal is not to reach a final destination, but to keep going deeper, to keep learning, to keep asking questions. The presence of human influence even here, the microplastics, the pollutants, the traces of industry, also reflect something about us. It shows how far our reach extends, how our actions ripple into places we have never seen. But it also reminds us that we are part of the system we affect. Just as our choices shape the trench, they shape the depths of our own lives. The habits we form, the decisions we make, the values we hold, they sink deep, shaping who we become in ways we may not always notice. And just as the trench responds to change over time, so do we. We adapt, we evolve, we find new balances. The creatures of Challenger Deep, from the snailfish to the xenophyophores to the invisible microbes, embody resilience in its purest form. They show us that life is not fragile. It bends but does not break. It finds a way in the most improbable places. It transforms obstacles into conditions of existence. That resilience is within us too. We carry it in our capacity to endure, to adapt, to rebuild. We carry it in our ability to create meaning even in darkness, to grow even under pressure, to find connection even in isolation. The abyss is not a place where life stops. It is a place where life proves what it is capable of, and so are the deep places within us. Even the trench's silence has something to teach us. Down there, sound travels differently. It is muted, slow, deliberate. There is no roar of waves, no chatter of wind. It is a world of stillness. In that stillness, life goes about its work. It does not need noise to exist. It does not need attention to thrive. It simply is. We live in a noisy world, full of constant movement and distraction. But the trench reminds us that there is strength in quiet, that depth is often found in silence, that growth can happen without fanfare. The most important processes, the cycling of nutrients, the folding of proteins, the formation of new life, happen unseen and unheard. The same is often true of us. The changes that matter most, the ones that define us, often happen quietly beneath the surface. The abyss also teaches us about humility in the face of scale. The trench is vast and ancient. It existed long before humans appeared, and it will exist long after we're gone. Its processes unfold over millions of years. Its ecosystems operate on timescales that dwarf our lives. Standing at its edge, we're reminded of how small we are. Not insignificant, but part of something much larger. This perspective can be grounding. It reminds us that our struggles, though real, are part of a much bigger story. It reminds us that we are connected to forces and patterns that stretch beyond our lifetimes. And it reminds us that we are not separate from nature but part of it, shaped by the same laws and forces that shape the trench. This perspective also invites gratitude. The fact that we exist at all, that life has persisted through billions of years of change, that it has adapted to everything from asteroid impacts to ice ages, that it has found ways to thrive in places like Challenger Deep, is astonishing. We are part of that story. Our cells share ancestry with the microbes that live in the trench. Our biochemistry is built on the same principles. The abyss is not just a distant place, it is part of the same evolutionary journey that produced us. In that sense, the trench is not just beneath the ocean. It is within us, in our DNA, in our biology, in the deep history that connects all life. Thinking of the abyss this way changes how we see it. It is no longer just a geographical feature or a scientific curiosity. It becomes a teacher. It shows us what resilience looks like. It shows us how life adapts, how it endures, how it builds complexity from simplicity. It shows us that depth, whether in the ocean or within ourselves, is not something to fear, but something to explore. It invites us to look inward with the same curiosity we bring to the deep, to ask what hidden worlds exist within us, what unseen processes sustain us, what potential lies in the parts of ourselves we have not yet explored. The abyss also reminds us that exploration is never truly finished. Even after more than a century of studying the trench, we still know so little about it. Each expedition reveals new questions. Each sample uncovers new mysteries. The more we learn, the more there is to learn. The same is true of ourselves. Self-understanding is not a destination but a process. It deepens over time. It changes as we change. It reveals new layers the deeper we go. And, like the trench, it rewards patience, persistence, and humility. In the end, the abyss is not just a place. It is a concept, one that speaks to the unknown, the hidden, the vast. It is a reminder that most of what exists, whether in the ocean or within ourselves, lies beneath the surface. It is a call to keep exploring, to keep asking questions, to keep reaching deeper. Because whether we are studying the deepest trench on Earth or trying to understand the depths of our own minds, the journey is the same. It is a journey into the unknown, one that humbles us, challenges us, and, if we are patient, transforms us. And so, as we continue deeper into this story, it becomes clear that Challenger Deep is not just a distant alien world. It is a reflection of something universal, a mirror of the forces that shape all life, including our own. It shows us that depth is not emptiness. It is potential. It shows us that pressure is not always destructive. It is formative. It shows us that darkness is not the absence of life. It is the space in which life invents new ways to exist. The abyss is not just beneath the ocean floor. It is within us, shaping who we are, waiting to be explored. The journey back to the surface is not just a reversal of the descent. It is something else entirely. After spending time in the trench, even if only in thought, the surface is no longer the same place you left behind. The light feels brighter, the air thinner, the sounds sharper. The world seems faster and noisier, but also more fragile. The return is not just about climbing upward through water and pressure. It is about emerging from one way of seeing the world into another. Once you have glimpsed what lies at the bottom of the deepest ocean, it becomes impossible to look at the surface the same way again. As you ascend, the darkness slowly lifts, though it never truly disappears from your mind. The pressure eases, though the weight of what you've seen lingers. The cold gives way to warmth, the stillness to movement, the emptiness to abundance. But even as sunlight filters back into the water, the memory of the abyss remains. You carry it with you. The knowledge of strange, ghostly creatures thriving in places once thought lifeless. The understanding of microbial kingdoms shaping the planet from the shadows. The awareness of how deeply connected the surface and the deep truly are. It is a knowledge that changes you in subtle but irreversible ways. Rising through the water column, you pass through worlds you now understand differently. The Twilight Zone, once a vague mystery, is now a place of transition. A realm where the last traces of sunlight fade and bioluminescence begins to rule. The Midnight Zone, once a symbol of emptiness, is now alive with meaning. A place where life has written an entirely different set of rules and flourishes by following them. Even the surface layers, teeming with plankton and light, feel different now that you know where their dead will fall and how those remains will feed the world below. What once seemed like separate realms Light and dark, surface and deep, life and void, now appear as parts of one continuous whole. The return to the surface is also a reminder of scale. It takes hours to ascend from the bottom of Challenger Deep, even in a modern submersible. That is because 11 kilometers is not just a number. It is an immense volume of water, a weight pressing on everything beneath it. As you rise, you realize that the trench is not a narrow fissure in the earth, but a vast and complex landscape, larger and deeper than most mountain ranges. It is a hidden world that dwarfs our daily concerns and stretches far beyond the reach of our senses. Knowing that such a place exists, and that it is still largely unexplored, changes the way you think about the planet. It makes Earth feel bigger, older, and more mysterious than it did before. And yet, paradoxically, it also makes Earth feel more connected. The abyss may be distant, but it is not separate. It is shaped by the same processes that shape the surface. It remembers the same events. It participates in the same cycles. The marine snow that sustains it is born of sunlight. The sediments that line its floor carry the dust of continents. The water that fills it is part of a global circulation that touches every ocean basin. The abyss is not apart from the surface. It is an extension of it, just as the surface is an extension of the abyss. They are two expressions of the same planet, bound together by gravity, chemistry, and life. The same is true of us. The deep places within us, the ones shaped by pressure, darkness, and time, are not separate from the parts we show to the world. They are connected. They influence our choices, shape our actions, and give depth to our lives. What we learn in those depths changes how we live on the surface. The resilience we build under pressure becomes strength in the light. The patience we learn in darkness becomes wisdom in clarity. The connections we forge in isolation become empathy in community. The descent and the ascent are not opposites. They are parts of the same journey, and each makes the other possible. The return is also an opportunity to see familiar things with new eyes. The sunlight that once seemed ordinary now feels miraculous, a rare and precious energy that does not reach most of the planet. The air that fills your lungs is no longer just background, but an extraordinary mixture that sustains complex life. The waves that break on the surface are no longer just motion, but the visible expression of a global system of currents and tides. Even the simplest things, a breeze, a cloud, a gull, take on new meaning when you understand how rare they are in the vastness of the ocean and the universe beyond. The abyss does not diminish the surface, it enriches it. It also deepens your sense of connection to the planet as a whole. Before, the deep ocean might have seemed distant and irrelevant, a curiosity with little bearing on your life, but now you know that it plays a vital role in regulating the climate, cycling nutrients, and storing carbon. You know that the microbes living in its sediments influence the chemistry of the entire ocean. You know that the particles that fall into its depths are part of a planetary circulation that connects forests and rivers, deserts and glaciers, volcanoes and cities. You know that the trench remembers our presence, not just in the pollutants that reach it, but in the very shape of its ecosystems. And once you know these things, it is impossible to think of the ocean as something separate from you. This shift in perspective extends beyond Earth. The trench has shown you that life is not bound to the surface, that it does not need light or warmth or abundance to exist. It has shown you that ecosystems can thrive in isolation, powered by chemical energy and patience. It has shown you that the conditions we once considered extreme are, in fact, conditions life can embrace. And so, when you look up at the night sky now, you see it differently. Europa is no longer just an icy moon. It is a world that may have its own trenches, its own invisible kingdoms. Enceladus is no longer just a distant speck. It is a place where chemical gradients may sustain life in the dark. Mars is no longer a dead world, but a planet that may harbour deep aquifers where microbes persist, hidden from the surface. The trench has taught you that life is not rare and fragile but persistent and creative, and that changes how you see the cosmos. It also changes how you see yourself. You're no longer just a surface creature, bound to the thin layer of light and air where most life is visible. You're part of a planet that extends far below your feet into places you may never visit, but that shape your existence nonetheless. The oxygen you breathe is regulated in part by processes that happen in the deep ocean. The climate that sustains your world is moderated by carbon stored in abyssal sediments. The nutrients that feed your food chains circulate through waters that have travelled through the deepest trenches. The trench is not distant. It is part of you, and you are part of it. Returning to the surface also brings a renewed sense of responsibility. You cannot unknow the fact that microplastics have been found in the guts of amphipods 11 kilometres down. You cannot ignore the evidence of chemical pollutants in the sediments. You cannot forget that even the most remote and ancient ecosystems bear the imprint of human activity. The trench remembers us, and it will continue to remember us long after we're gone. This knowledge is sobering, but it is also empowering. It means that our actions matter, not just in the places we see, but in the places we do not. It means that we have the power to shape the deep, for better or for worse. And it means that caring for the ocean is not an abstract ideal, but a practical necessity. That responsibility extends to exploration itself. As we build more advanced submersibles and send more machines into the deep, we must do so with care. The ecosystems of Challenger Deep are fragile and slow to recover. A disturbance that seems minor at the surface can persist for decades or centuries below. Sampling must be done thoughtfully. Equipment must be designed to minimize impact. Data must be shared widely so that our understanding grows collectively. The deep ocean belongs to no one and to everyone. It is part of our shared heritage, and protecting it is a responsibility we all share. But responsibility does not mean fear. It does not mean we should avoid the deep because we might harm it. It means we should approach it with respect, with the same respect we would offer to an ancient temple or a priceless work of art. It means we should explore it not as conquerors but as students, eager to learn but mindful of the consequences of our actions. The trench is not a frontier to be claimed. It is a teacher to be listened to, a partner in our ongoing quest to understand the world. The return to the surface is also a return to the questions that brought us here in the first place. Why do we explore? Why do we seek out the unknown, even when it is difficult, dangerous, or distant? The trench offers many answers. We explore because we are curious, because we want to understand how the world works, because we are driven by the desire to see what lies beyond the next horizon. We explore because each discovery leads to new questions, and those questions drive us forward. We explore because the act of exploration changes us. It expands our perspective, deepens our understanding, and enriches our experience of the world. And we explore because, in doing so, we find ourselves reflected in the places we study. The trench is alien and remote, but it is also a mirror showing us the resilience, creativity, and persistence that lie at the heart of life and at the heart of us. There's another reason we return to the surface changed, because the deep is humbling. It reminds us of our smallness in the face of nature's scale. It reminds us of how much we do not know and how much we still have to learn. It reminds us that the world is older, larger, and more complex than we often imagine. And humility, far from being a weakness, is one of exploration's greatest gifts. It grounds us. It teaches us to listen. It reminds us that knowledge is not something we possess, but something we pursue. The trench also teaches us wonder. It shows us that there are still places on Earth that remain mysterious, that there are still questions we cannot answer, that the world still holds secrets worth uncovering. In a time when it often feels like everything has been mapped, measured, and explained, the abyss reminds us that mystery is alive and well. It invites us to keep asking, to keep seeking, to keep believing that the unknown is worth exploring. And it shows us that the unknown is not just out there, in distant galaxies or alien planets. It is here, beneath our oceans, beneath our feet, beneath the surface of the world we think we know. The ascent ends where it began, at the surface, where light dances on waves and wind ripples the sea, but you're not the same as you were when you started. You have seen a world where pressure is measured in tons per square inch, where darkness is complete, where life thrives without sunlight. You have witnessed ecosystems built from scarcity and patience, microbes that turn stone into sustenance, animals that embody resilience in its purest form. You have seen the deep ocean not as a void, but as a cradle of life, a storehouse of history, a frontier of possibility. And you have seen how deeply it is connected to the surface, how much it shapes and is shaped by the world above. The return is not an ending. It is part of a cycle. Descent and ascent, question and answer, mystery and understanding. It is a reminder that exploration is never finished, that each discovery opens new paths to follow. It is a call to keep going, to keep asking, to keep reaching deeper, into the ocean, into the earth, into ourselves. And as you step back into the light, the abyss does not disappear. It lingers in your mind and in your senses, a presence that will not fade. You may never visit Challenger Deep. You may never see its ghostly fish or its invisible kingdoms, but it is part of your world, shaping the air you breathe, the climate you live in, the life you share the planet with. And in that way, it is part of you. The surface and the deep are not separate. They are parts of a single whole, as inseparable as light and shadow, as day and night. The story of Challenger Deep is not just the story of a place, it is the story of connection between surface and depth, between geology and biology, between Earth and the cosmos, between the world outside and the world within. It is a story that reminds us of our planet's vastness and complexity, of life's resilience and creativity, of the power of curiosity and exploration. And it is a story that, once heard, changes the way we see everything else. When you look at the ocean now, you know that its surface is only the beginning. Beneath it lies a world deeper, darker, and more intricate than most of us can imagine. A world that shapes our planet and reflects it back to us. And when you look inward, you may find something similar. Depths you have not yet explored, pressures that have shaped you, hidden forces that sustain you. The abyss is not just out there, it is everywhere. Beneath the waves, beneath the ground, beneath the surface of our own lives. And so the journey continues. The surface is not an endpoint, but a place to pause, to breathe, to reflect before the next descent begins. There are still questions to ask, still mysteries to uncover, still connections to trace. The ocean still holds secrets, the planet still holds surprises, and we still have depths to explore in the world and in ourselves.